We do, but it's already, your presentation's already, yeah.
Oh,
Yep. Yep. Here you go. Check. So, Ben? So he responds to ask if he can use swap out his laptop. He's not the first speaker, he's the second speaker. Let's use a laptop. If you won't mind grabbing it, we'll do a quick test to make sure it looks okay. Okay. Absolutely, you and me both.
Tried to show you my door is open. I don't know how much more I can take since you've chosen to leave me frozen. Am I the only one who sees what you become? Will you drift
Ben, I'm going to test his.
We're running out of time. Two ones can make it right. Could I make you stay? People making choices.
Okay, good. All right, we'll just do that. Perfect. No worries. I grabbed this out of the thing. I grabbed this out of the bag. If you can grab it in the next 4 minutes. Great. If you want to grab it, yeah, that'd be great. One, Martin. Decaf, right? Good. Progress.
Michael. Is this the one for this one here? Yeah, the other one? There you go. This one's a green laser. Private.
There's your new presentation here, and then there's the guy after him. Do you want to introduce the next speaker out here?
No.
What's that?
I need to run to the
Okay, okay, that's fine, that's fine. Okay, so I'll introduce Tom and Jim.
You don't love me, even if you say you do.
Leave it up here.
You don't deserve me. Don't treat me like a fool. Treat me like a fool. Don't treat me like a fool.
Yep.
My last drop.
Yep. Okay, very good.
All the moments that we spent together are worthless. All the promises that we gave each other mean nothing to you. You're a devil. You broke me into pieces. You're a murderer. You kill me when no one believes it. No, no. You don't love me, even if you say you do. You don't deserve me. Don't treat me like a fool. Treat me like a fool. You don't love me, even if you say you do. You don't deserve me. Don't treat me like a fool. Treat me like a fool. You don't love me, even if you say you do. You don't deserve me. Don't treat me like a fool. 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 Don't treat me like a fool.
What's that?
There's a lot of change at the moment, but there are two monster trends changing everything. One is that cloud is becoming real, and the second is that solid-state storage is displacing spinning disks. And both of those have profound repercussions across the industry.
The most disruptive trend that's recently happened was the advent of flash technology. So that's really changed the entire dynamics on how we do storage.
The new data center could be quite a bit different than what we're used to today. The traditional local storage in a corporate data center is likely to decline.
But there are a significant number of companies that are still building data centers, that are still populating them with perhaps their own storage systems that they build from commodity components.
With any new technology, a new horizon, there's a lot of people saying what's going to happen next.
You need to understand, is this something I need to worry about right away? Or is this something that's going to take a while to be adopted?
Non-volatile memory is the next progression in storage. NVMe, I want to learn a bunch more about that. That's where we're headed next. What we're working on now is likely to be an interim step towards that next change that we'll need to address, and fairly quickly.
There are a number of new technologies emerging that go beyond the current capabilities of flash, but they require some changes in the way applications and other types of software manipulate those technologies.
I see software becoming a solution that the enterprises continue with, and then the broader market in general is still enamored with appliances. And so I see both the appliances still marching ahead the way they've been, and then the enterprise focusing on software.
All this is leading to huge amount of change, not just at the storage vendor perspective, but also at the end of the customers on how they're looking, managing and implementing storage looking forward.
There is a lot of overlap for a lot of these technologies. When it comes to the latest technologies, including solid state drives or non-volatile memory or non-volatile memory express, the NVMe stuff that's coming down the road, or fiber channel with the advances, they all intersect. We can do NVMe with fiber channel, we can do Rocky with Ethernet, and iWarp with, with these types of technologies. Putting this all together into a meaningful fashion is very important.
How can we bring all of these together to produce the next generation of storage management API?
There are a few places that you can go in the industry and get peer-reviewed, vendor-neutral information about new technologies.
Good morning, everyone. Welcome to SNIA's 20th Storage Developer Conference. We're excited to have you here today, not just those in the room, but also those who unfortunately couldn't make it in person today and are watching us live streamed right now on YouTube. Quick bit of housekeeping before we jump into today's sessions. Wanted to just remind everyone, I know many of you have been involved with SNIA for the last 20 years, but some of you are new. So just want to take a quick recap on what is SNIA about. If you were going to go click on About, what would summarize SNIA? Standards, those who are most familiar with. We'll go into some more details in a later presentation what some of those standards are. Plugfests and our conformance test programs. Again, you're seeing just here at the event this week, we have 3 different Plugfests that are going on. We'll cover a bit on those as well. Technology initiatives as well. When we have new initiatives that come to the marketplace, companies have come together to provide education in the form of the initiative output and also the formal SNIA education programs that we have, along with certification programs as well that have been long-standing in the marketplace now that are vendor neutral and available for those that are just starting in their careers in the storage industry and those looking to take some of the advanced level certifications as well. And of course, the SNIA event, you are at one today, and hope to see you at other ones throughout the year, both in person and as we've adapted with the industry and travel considerations for many of you. We do a tremendous amount of webcasts, Bright Talk, and other platforms that we stream. Please, if you haven't joined yet to the distribution list, if you haven't subscribed to SNIA, if you're not receiving SNIA Matters, we'll fix that this week. A big thank you to all of you who are here as attendees, to all the speakers and all the sponsors. It's great to see the continued commitment of the storage industry vendors in working together and bringing these type of events to you, bringing us together so we can talk about not just the challenges of today, but what we need to be doing together tomorrow. In terms of schedule for today, general sessions, which we'll be starting briefly here, will be in this room through noon. In terms of lunch, we'll be out on the mezzanine. Please do get a chance to circle around, talk to our sponsors that are in the mezzanine area. Then the breakout sessions will commence at 1 o'clock through 5 p.m., at which time we'll have a networking reception. Again, an opportunity to talk with our sponsors, learn about their product and services. Many of them are showing for the first time new demos and solutions that were intended to be shown at Flash Memory Summit, and they're getting a first chance to show them publicly here at SDC. So we're excited to have those showing those technologies here at SDC this week. And last but not least, please do join us for the Birds of a Feather sessions. These are sessions which are the early conversations of new standards, new technologies, new considerations that we as an industry have to tackle. Many of our projects start in that form, and we started last night with 2 Birds of a Feather session, very well attended, great excitement and energy there. Look forward to continuing that the rest of this week. So please look for those and please do join. And as a bonus for those present, they tend to at least provide some beer, so enjoy that after hours. If you haven't downloaded the Storage Developer Conference app, please take your phone out, not just to put it on mute for the sessions, but actually to download the app. You're able to scan the QR code here. It's available in front of the registration desk. And of course, you can also do it from the link that you've been sent with your registration for the event. And if you go on to the app stores, please search by the full name, Storage Developer Conference, and the app should pop up there. Be able to follow, create a customized schedule for yourself throughout this. Make sure you don't miss anything. One of the changes you should have seen in our conference this year, we've actually gone full day on Thursday in order to try to minimize the amount of overlap in sessions and give you an opportunity as much as possible to attend all the different sessions that you have an interest in. You'll also be able to see more information on the speakers. And one of the cool features as well, be able to see those people selecting their itinerary, who is actually attending sessions. If you're looking to network, find someone, it's a great app for that perspective as well. So please make use of it. Please give us your feedback on it so we can improve and make sure it's the best tool maximizing the time that you are spending here with us this week. Tweeting, please, we're encouraging you to tweet about SDC this week. Please use the hashtag SDC17 throughout the week. We are monitoring those, promoting them as well, and so there is going to be an award, Intel SSD drive, and if you guys really contribute highly on this, I'm sure we can work on trying to get you an Optane drive next year. So. Again, I mentioned the Plug Fest that we have going on this week. A big thank you to the underwriters and participants of the long-standing partnership with Microsoft and NetApp who are underwriting this Plug Fest. You can see the list of companies that, the impressive list of companies that are listed here that are downstairs plugging away at the SMB3. Also, the Cloud Interoperability Plug Fest is happening this week as well. A big thank you to the Cloud Storage Initiative Group for sponsoring that and driving those activities forward. Last but not least, the SMI Lab is the other underwriter for the Plug Fest this week. A lot of great work, not just on a very successful SNIA spec with tremendous implementations, number of implementations in the industry on the SMIS spec, but also a new up-and-coming spec in the space with RESTful APIs and all sorts of exciting collaboration opportunities with the DMTF on the Redfish spec. We are, of course, doing the Swordfish spec, and we're starting to see the first of those implementations and PlugFest activities around it. Quick recap on the general session speakers for today. I'll be providing a quick overview on what SNIA does, take a retrospective on the last 20 years, since we're celebrating that milestone this year, and through that experience, trying to draw a line out on the possibilities and where we're headed for the next 20 years. 9:45, Memories of Tomorrow. Tom Coughlin and Jim Handy will be following. Quick break after that, just to allow you to grab some coffee and bio break as needed. Sage will be up on stage on a Goodbye to XFS speech, and followed by that, Martin will be up here on recent development in the Linux I/O stack. Please attend those sessions. Again, birds of a feather sessions for today. Mentioned that those are starting at 7 o'clock today. Mark Carlson will be hosting the first one on data center storage update and futures, and followed by Eden Kim on understanding real workloads today I actually apologize. Those are running in parallel today, so you'll have to choose between them and your interest, as opposed to last night we actually ran them in series. Evaluations. We are here as an organization for you, the members and the attendees of this event. Please give us your feedback. Not only it's an easy $100, you'll have a much better chance of winning $100 than you will the California lottery. But highly encourage you guys to participate. Give us your feedback. We need to know not just what we're doing poorly. Yes, we always want the feedback on what we can improve, but we love to hear from you on what we're doing well so we can continue doing that for the next events. So with that, we'll wish you a great event. Many of you are here the second day for the event, and look forward to interacting with you, not just in the sessions, the tremendous agenda that's been prepared by the agenda team, and we're very excited to have you here. And I'll jump into the first presentation. So as we try to look at the future, I found it best to and necessary to look at our past, look at our history, understand where did we come from, what were some of the learnings, what were some of the milestones, what trajectory are we on? No one can predict the future, especially in technology 20 years out. I'll be clear about that, and I'm not trying to stand up here and tell you that I know what's going to happen 20 years out. But with the experience of the last 20 years in the storage industry, we can start looking at those trajectories and what is possible. And some of that is driven by the choices, the very choices that we in this room, the companies that we work for and represent, make every day on our new projects, new technologies, new standards, how we drive them. Are we doing collaboratively? Are we doing open? Are we truly working together as an industry for the benefit of our end users? So, how did we get here? Well, it really started about 40,000 years ago. As many of you know, we had carbon-dated cave paintings that have been found dating all the way back to 40,000 years ago. Those driven by human nature, socializing, seeking shelter, being together, spending time indoors, and trying to depict how we lived our lives. Those are followed by pictograms about 9,000 years ago. Those, as cities and larger groups of people were living together, they found the need for being able to identify produce, constructions, buildings, and they would do those through pictograms. Then 5,000 years ago came writing. And interestingly enough, as the population of the world had increased on all of the continents, this one, if you look at the history, is kind of claimed by, you could see where parallel invention of writing really happened on 3 different and distinct civilizations, from the Sumerians and Egyptians about the same time frame and somewhat in the same area, to China, to what then became the Mayan culture and empire. Overall, what did that drive us to? It still wasn't until about 300 years ago that paper itself was used for data storage. What do I mean by that? Because the first implementation of this was really used for some of the yarns in France to be able to actually automate things. It wasn't actually storing data, it was storing a set of instructions, essentially. It was about another 150 years later until we actually did have data storage, where we did the punch cards, data cards, where we actually stored information that machines could then read. And then subsequently, the next big milestone in how we got here is commercial electricity. All of our electronics run on electricity. Without this one, we would be not streaming on YouTube today. So from there on, what happened? Well, about 70 years ago, actually this year, it'll be 70 years, transistor happened. Hard disk, 63 years ago. Network storage, 34, 33 years ago, depending which one you kind of look at from the Novell or Sun perspective. Flash memory. Toshiba brought that officially to market 33 years ago. Storage area networks, 23 years ago. Okay, maybe I'll say 21, 1996 when 1 gigabit fiber channel really kind of took off and hit the marketplace, and then continued doubling its speed every few years since to date. And then SNIA happened. The organization overall formed very, very shortly after some of the very first fiber channel devices came out, recognizing that this is new for the industry. There was a need for education. The companies that were bringing these technologies to market came together to provide that platform of education to the marketplace, collaboration on training, and the standards that were needed for conformance, interoperability of those products, and many, many, many more things that SNIA has done since. So, let's talk briefly on why standards are important. I'm going to pick on one of those things from that list of the previous pages of what we come around, and use electricity as an example on why standards are important. Well, first, this started with a big battle, a battle of the currents, if you would, and between AC and DC currents in the late 1800s. Well, 2 driving forces between Edison and Westinghouse. They're essentially both had their own ideas. They saw their own benefits of direct current versus alternating current. And, well, eventually, on that one, AC won out. Why, primarily? Without getting into the politics and the fun back and forth of that time frame, was essentially distribution. How do you efficiently distribute electricity over long distances and then be able to bring it not just for outdoor applications, which was some of the first implementation of electricity, but also for indoor use in homes, and of course, in the industry. So, a little bit of the history of what happened there. We ended up with 2 different set of voltage ranges that occurred. We kind of standardized on overall. One, you'll find it throughout Europe dominantly, and the countries that were connected and did business historically with Europe, and the other in the US, and the rest of the world that mostly dealt and bought products from the US. Well, on the frequency side, it's a little bit of a more complicated and worse story, because at the very beginning, there were up to 14 different frequencies that were implemented in this, and there wasn't a standard around this. Well, eventually that settled down to about two principal ones, 50 and 60 hertz, but even some of the less popular ones from a generic application perspective, like the 25 hertz, those were alive and well and still had commercial production all the way up until 2009, if you believe it or not. So out of those even, you think, okay, that kind of came together, great. It was a big mess at the beginning, but we've got four permutations, essentially, that we have to live with today in the global marketplace. Well, I have to throw in one more mix in there, the fact that there's 15 different plugs, depending where you are in the world, for connecting to that power outlet. So what's the impact, right? We started essentially with big innovation, big change. I mean, again, the whole high-tech sector essentially would not exist without electricity. So it's fundamental innovation that was brought to us in the late 1800s, in the 19th century. But what was the impact of the fact that there was no standardization up front? Well, if you look at just cities, for example, in the early 1900s, like London, they had up to 10 different frequencies in there. And we'll talk a little bit about, in a moment, why that's important and the impact that it has on not just not allowing things to work, but in many cases not working the way they're supposed to. So the electronics industry today, all of us travel with our laptops, cell phones, everything else. We're like, hey, we don't really see what the big deal is of not having had standards here because, well, the electronics operate on DC power. So the joy of the manufacturers has been to provide power supplies that can adapt to all of these different permutations and provide us that freedom of just find one of those 15 plugs that I have to figure out how to get into the power outlet. That's simple enough, right? But even today, the electric machinery and motors that are out there in operation are a different story because they don't operate on DC. There isn't a conversion sitting in front of them, so they very much have to be designed for the respective voltage and frequency. Well, that results in higher costs for people, right? Not just for the manufacturers who initially, if you look at the history, right, started to protect their marketplace between the companies in Europe and Germany that were the predominant manufacturers and suppliers of electric appliances back in the early days, and Westinghouse Electric in the US. But now, for those machines, you still, to the state, have to keep different SKUs that conform to the respective voltage and frequencies. That's a higher cost for manufacturers. Managing your inventory is that much more challenging when you have a proliferation of SKUs. From a consumer perspective, choice is a challenge. If you're moving, you have to kind of consider what you're willing and what you're not willing to take with you. Of course, much less likely to be taking your washing machine from the US to Europe, but in the areas where throughout the world, they are neighboring countries that do have different frequencies or voltages. And for the ladies out there in the audience, your favorite hair dryer, well, you're buying a new one at that point because it's not going to function properly. But you say, okay, but we've kind of somewhat managed, so why are really standards that important? Well, let's look a little bit deeper for an example. LA Power Grid is an example. In the early 1900s, when the power grid was set up for LA, there was no standardization There was standardization on voltage in the US or general agreement, but there was no standardization on the frequency. So the LA power grid was set up on 50 hertz instead of 60. You say, okay, well, it's close enough. Why the big deal? Well, all the way up until 1945, LA was operating on this different power grid. And again, you say, well, okay, fine, whatever, what's the big deal? Well, if you moved from New York to LA and you brought your clock with you and you plugged it into the wall in your brand new home in LA, you would be consistently off base about 10 minutes every hour, in fact. Not to mention your lighting fixture and other things would be problematic. So, okay, fine, you buy new ones. You kind of have to go deal with it. But easier example of you love to listen to music. You were in San Francisco, moved down to LA, bring down your record player, plug it in, and all of a sudden you're getting a very nice and deep voice coming out of your player. Well, it's spinning at a reduced rate because of that frequency. So the power grid company in LA eventually had to make the change and standardize to 60 hertz. That process took them 3 years. During that time frame, it cost them more than $30 million back in 1940s. That was a lot of money. In fact, that was a third of their gross annual revenue that it cost them to set up exchanges for clocks, lighting fixtures, refrigerators for 750,000 people in LA, which certainly wasn't the number of people that they started with and were supporting back in the late 1800s. So these are the consequences that we have to consider when we are pursuing implementations around new technologies. And that is why organizations, not just the SNIA to drum our beat, but in general, companies coming together and discussing and having these considerations up front is important. Otherwise, it will cost you down the line, not to mention the 9 phases that the power grid company had to manage in order to make that transition over 3 years. It's a huge, huge impact in time sink, not just for the company, but for the individuals of that city. So you say, okay, great, but that was, about 50, 60 years later after, and it's been some time. What's the big deal now? Well, it's a quick look at Japan's power grid. Everyone remembers the unfortunate event and tsunami in Japan, which affected millions of people and the power grid in that country. What it brought to attention was the fact that Japan had been operating since the early 1930s when it made its acquisitions of its power generators and set up their power grid, that they were operating on same voltage, different frequency. So the side of Tokyo and east side of Japan essentially was operating on equipment that was purchased from Germany, operating on 50 hertz. The west side, Osaka, set up their grid, was set up on US GE purchased equipment, which was 60 hertz. Great, operated, no issues, considerations. They were able to manage that, just peachy for the most part, until this event occurred. And they operated that way for 80 or so years. The impact of that was when they were forced to by the event, the power production on the east side of Japan and to Tokyo specifically was severely, severely impacted. This reduced their ability to operate data centers in Tokyo, having to move capacities for their operations to the west side of Japan, to Korea, to US, and other parts of the world. Rolling blackouts throughout the city and the area that would have to be managed because of this huge shortfall of power. But kind of the insult to the injury here, if you'll allow me, is the fact that the west side of Japan had the capacity, production-wise, to actually supply near peak demand what the east side of Japan, Tokyo, and the rest of the east side of Japan needed. But when you have this type of incompatibility, this invisible line that divided Japan from a power grid perspective, it caused a huge, huge issue. It takes normally 18 to 24 months to be able to spin up and bring up new power capacity to a country. This was non-trivial. And the fact that you had it right there and not being able to use it because of this was, again, a reminder why a little more discussion and standardization up front in the early years would have helped to avoid some of the additional and unnecessary problems that this caused. Of course, you say, well, you can convert those things. Yes, there are ways of converting between the two, but whenever you have to do conversions, you're losing power. You have to go through what we would think of as an API or a converter, right? So you can convert the AC from one side into DC current and then from DC back into AC at the right frequency. But capacity for that was extremely limited in Japan. The cost for bringing something like that up was highly inefficient, and it takes time to be able to do that. So once again, facing a situation that could have been avoided with forethought planning. And I bring these up for us to think, again, all of the technologies that we work in the electronics industry, based on power, is a fundamental enabler. And in many cases, we still haven't learned some of the mishaps over the last 100 years of not standardizing on power. So let's take another perspective on the last 20 years and how far we've come. These are name brands, companies, devices that we are all familiar with. They're part of our life. They're in your pockets. They're on the desk. They're at home. They are everywhere. How many of these companies were around in 20 years ago? Well, it started 5. Pokemon Go, Apple Watch, Microsoft Surface, Amazon Echo, not around. 10 years? Well, no iPhone, no Waze, no Lyft or Uber. 15 years ago? Sorry, no Facebook. Those photos that you're hoping someone 40,000 years from now will be able to see them, just like those cave paintings. Sorry, you better have them stored somewhere else. 20 years ago, big names. No Google, no DVR, USB, things that I'm sure everyone's got at least one, if not 2, USB drives in their pockets and other devices. Netflix, BlackBerry, Alibaba, so many others that on there did not exist 20 years ago. Why did I choose to kind of take this look at these brand names just, again, to solidify in our minds just how much we've achieved in the last 20 years? But part of the reason I did, which of these are data center dependent? That without data center technologies, which SNIA and the respective companies in this room have enabled, how many of them would not exist without data centers and the fundamental technologies that are in place there and that we're continuing to invest presently? They're highlighted in blue there. It's an interesting perspective to understand the fundamental impact that we as developers have on everyday life in the world. And if we are to look ahead, I am willing to bet that some of these companies on this list will not be on this list 20 years from now because other new innovators that are taking advantage of the technologies that you are working on standardizing and developing today, they're adopting and they're going to outpace the current leaders. So, a little bit about SNIA and what we do. Flash is on the top of everyone's list. Everyone is flashing left and right in every which direction nowadays with new media, new interfaces. It's definitely hit the mainstreams in terms of workload, and it is the innovation focus for the industry. Persistent memory, well, we've talked about that and how it is going to fundamentally change the computer architecture model that we're familiar today and how software is written and interacts with some of those systems. And again, I mentioned earlier, those that will innovate, they'll be able to bring out new products, new services to market based on these capabilities and innovation that we haven't seen yet. There are not just startups in the storage industry, but it will be new startups that we will see over the next 20 years that take advantage of this technology. They'll bring to market things that we haven't even thought about yet. Of course, doing this, the emphasis on developing responsibly, what we do on the green front. SNIA has been doing great work on that with, in the US with EPA and around the world with the work on Energy Star program, but the Emerald program that SNIA has, is leading and has brought to market as a standard. On the security front, while there is specifically a security twig, at SNIA we take an approach to looking at anything that we bring to market. What is the security consideration for it? Persistent memory, for example. We're looking at that. What are the security considerations that we have to take into account? It's different than storage today. We have to look at, we can't apply the same security principles and assume they work in persistent memory applications and implementations. Object drives, we'll talk a little bit more about that in some upcoming foils and some of the companies that have joined and contributed to SNIA and as well on cloud. Our standards that exist in there, while have seen great traction in Europe in particular, where the EU government is making some mandates and looking at where they would like to see cloud go and what standards, wherever standards exist, they are essentially looking to dictate and bring those in order to ensure interoperability of services to the government and to the rest of the companies in Europe. On the management front, I already mentioned the SMIS and the new Swordfish standard that is now been published, and of course working on the next rev already, constantly innovating and looking at what the industry needs moving forward. In terms of members, we have about 160 companies around the world, 2,500 active people in SNIA contributing in some form of somewhere around the world in some form or another. And we also have 50,000 people that are subscribed to our newsletter and interact and consume our content that is published, webcast, emails, news specs, everything else that is publicized and shared by SNIA. So, in terms of the last 20 years of standards development, well, we've taken many of these SNIA specs and hadn't become ISO and ANSI standards. Some of them remained as storage standards that are adopted and implemented by companies as are best practices in security. And, well, you're wondering, well, what are some of those standards? It's a long list. We would be here for quite some time if I were to take the opportunity to walk you through each and every one of those. But each and every one of them has a life cycle. It comes, it gets adopted, implemented. Some of them are continuing mainstream spec and standards today. Some of them have been retired, and there will be constantly new ones that we are working on. That is the industry we live in. For those of you that are not familiar, in July of last year, another group in the industry who was driving standard joined SNIA as a new membership category that we created last year, technology affiliate. This enables other groups to essentially come and operate under SNIA, have the benefit of the organizational structure that we have, the IP policy that we have that is well reviewed and has been beat up from a lot of different angles by a lot of different companies. And just in the last year plus that they've been under SNIA, 9 new specs that they have implemented and rolled out in the industry. So, say that sounds great, but I'm not sure how do I make things to be a standard? How I see the list, you'll see the list on what we're working on, but I have this idea. How do I get engaged? As I mentioned earlier, we are here for you. If you have a new idea, new direction, new technology that you think is important to the industry, all it requires you're a SNIA member, find 2 friends in different companies, and a provisional TWIG can be approved where resources can be applied and start getting your message out as to what are your thoughts, start formulating a plan, and see how you get other people in the industry to join you, start developing that standard, and then we have a whole process and infrastructure in place on how those are driven into ISO or other standards as necessary and appropriate. Contact information there if you need help. You're not alone. We're here to help you through that. In terms of specifications, we're currently actively working on quite a few different specifications. On cloud front, CDMI is the cloud management data interface, IP-based drive management, key value APIs, LTFS. I know a long time ago people said tape would be dead, drives would be dead. Well, media industry and others, even for cloud onboarding today, are utilizing LTFS based solutions to move large sets of data in between physical locations. The NVM programming model I've already mentioned, and the impact that is having on system architecture and how we think about things. As storage developers, we have to understand that our brothers and sisters that do software development don't always think of what is the impact of new technology coming in the marketplace. And this is a very fundamental impact. I won't go into the details because there have been and are several sessions that go into what we're doing there, why it's important, and the fact that new work is happening on persistent memory over fabrics, which is how do you get outside the box. SURF is another one of the standards, the SNIA Emerald program I've mentioned. There are performance tests and specifications for that are under the SSSI group. The SMI and Swordfish, those I've already mentioned, all active projects within SNIA presently. The SFF groups I mentioned, they're working on connectors, transceivers, form factors. They presently have 17 different projects that are active today. So please look on the website. We have various vehicles where those projects are announced and communicated to SNIA members and non. In terms of open source, not too many people, but I'm hoping after this presentation and as we continue to get the message out, SNIA is involved in open source software. And we have several active projects there. And as listed, the API emulator for Swordfish. On the Swordfish side, we've done 3 different reference implementations to be able to test our implementation of the spec and help accelerate the development of the next rev of the specifications and help companies to implement this spec in their new technology and offerings. CDMI reference implementation is also one that is part of the open source software. And just to bring out, we enabled last year a methodology by which you do not have to be a SNIA member to participate in our open source projects. Essentially, it's a contributor license agreement that as a non-member you would sign, which ensures that your contributions are properly handled and making sure that it doesn't cause problem for the spec later down the line in terms of IP and other considerations. So we have that mechanism in place. In this case, we actually had a company, Indigo Data Cloud, that took that reference implementation, implemented, essentially took it out as a fork, implemented additional feature sets that they had an interest in, but then they took that back and contributed back to SNIA, enriching the feature set that is now available for everyone else to build on and evolve that spec. Another success story on CDMI is Philips Research. So Philips was facing a problem in their medical services side, and they looked to CDMI as a solution. They embraced that solution, joined as a member. They're an active member of the spec, and that's the beauty of not just consuming the specs after they've been published, but actually joining as an active member of the community. Then you're not faced with having to eat what was cooked. You actually get to play in the kitchen, provide your own ingredients and preferred method. So encourage you to become active, because that is how you're going to get what you want in a faster way, and then ensure that your products will be interoperable with your fellow teammates in the storage industry. Other projects, we do have a repository for I/O traces, tools, and analysis. Those are heavily utilized by students and the education community. DPCO is looking at a 100-year archive in the middle of a assessment or survey there to help enrich and provide the direction and output of that group. And if you attended one of the Birds of a Feather session last night on workloads, provisional twig that had been assessed, again, as I mentioned earlier, we talk about what we're going to do. We don't hide it. We invite you to participate, because that is how we successfully move things forward together. We also publish our draft specs. This is a current list, URLs at the top. encourage you to go take a look at our draft specs. Realize that some of you aren't members, but the importance of doing this is, did we miss something? What is the impact? Are you working on something that's relevant to this that should make you join either to adopt the technology or standardize or bring a new work into the work group to further advance the respective specs and technologies? So please check them out, please provide feedback, and get involved. So that's what we're doing. Where are we going? What are we facing? We're literally facing an avalanche of information that is coming at us, both as developers, as consumers, as individuals. And there's a lot of things that are contributing to this avalanche of information that we're facing, right? From Moore's laws, continuing to provide higher performance, drive costs lower, drive power lower. That's more precipitation just building up for this avalanche of information. IoT. Every little new gadget and device out there is generating, gathering data that has to be stored, analyzed, monetized in some form or another. And you think those devices are many right now? Well, 5G is going to make that explode to the next level, because that will connect at lower power, higher bandwidth, a bunch of devices that we haven't even thought of today. VR and AR, if you look at the raw bandwidth or data that some of these solutions require, we're talking upwards of 23 gigabytes per frame for some of these immersive capabilities that people are thinking of and piloting right now. Smart cities, AI, all these things that are generating more and more data that has to be stored, analyzed, and sorted. Well, just some more examples to kind of put that into perspective and numbers for you. In February of this year, statistically, there were 500 hours of video uploaded every minute into the social media feeds. If you look at our Defense Department capabilities, just looking at our drones, those are capable of capturing 430 petabytes of data per day. We talked about IoT, 5G, what that's going to bring. Well, predicted over 20 billion connected devices by 2020. We're 3 years away from that. And if you're looking at the surveillance market in terms of video capture there, another 2+ exabyte of data per day that is being generated. I think we're in the right marketplace for storage. We have some challenges ahead of us, but the good news is there's high demand for it and for what we are doing, because trying to manage the amount of data that is being generated using yesterday's technology or mentality is just not possible. It is not sustainable, but whether you embrace and accept that or not, that data and that avalanche, it is still coming straight at you. So with that, in terms of what's next, there's lots of things that are next. And I put a few of the things on here, and I'd love to talk, hear feedback from you in the hallways in between sessions, at the sessions, email, join as a member, call us up, send us an email, grab us any which way possible through social media and interact with us and give us your thoughts and feedback. But the list of challenges that we face over next 5 years, 10, 20, are enormous. And the only way we're going to successfully overcome those is by working together and collaborating with one another, as opposed to not doing that, because as you saw in the example that I gave on the fundamental and just electricity alone, the potential pain later down the line of not doing the right things up front is severe. So please join us. We also recognize that many of the companies that have been members of SNIA for 20 years or such, well, many of them are bigger companies than they used to be. They've grown, been successful, as SNIA itself has been successful in the marketplace. But there's new startups, there's new technologies. We want to make sure that there wasn't an entry to barrier for those startups to participate and be active members of this community. So we created a new membership category for startups. Essentially, if you've been around for less than 4 years as a company, you can join SNIA for up to 4 years until you yourself are successful and cross that 10 million annual revenue mark. So if you're in the audience, if you're watching on YouTube and you're a startup and have any touch point on storage, please join us. This $1,000 is the annual membership fee. It gives you benefit for attending our events, sponsorship to get visibility through all the mechanism that SNIA has, and more importantly, gives you an avenue for that technical learning and interaction with your peers in the industry before specs are rolled out in the marketplace. So, last but not least, I want to make sure that you've all seen it on the calendar for Wednesday night. Please join us. We have great celebration planned for 20 years of hard work that all of you have been doing, and we are proud and humbled to be here to serve you. Again, please always give us your feedback, bring us your ideas, and let us know how we can better serve you as members of this organization and how we can drive forward the innovation in the storage industry. Thank you. Hope you have a great rest of the day and look forward to your participation and feedback.
You got to plug into that cord. He's got it. Got it. Yeah.
So I'm gonna.
Ooh, yeah. Do you want to leave that up here?
I'll leave that up here.
Okay.
Okay.
Go ahead and start it.
Okay. Hello, can you hear me? No. It's not on? Okay, hold on. Now can you hear me?
Ooh.
Good. Howdy, folks. I'm Tom Coughlin.
I'm Jim Handy.
And we've often given some talks together at SNIA events, for instance, the January event, and we get a chance to do it again. I want to thank SNIA and the Storage Developers Conference for giving the opportunity to talk with you folks. And we're going to talk about the memories of tomorrow.
So Tom and I are both industry analysts. One of the things that we have to do for a living is to forecast the future, and usually we go out like 5 years, in some cases only 1 year. But you know, we thought, you know, this is an opportunity to really talk about things far out in the future. And Tom's got a couple of sons in college. I've got kids who are just out of college. You know, we were thinking about what are things going to be like for them way out there. So we said, you know, let's say 2075, you know, pretty far out in the future. Tom's a big science fiction aficionado, you know, likes all the Star Trek and stuff like that. And, you know, so we put our heads together and we said, what is life going to be like for our kids out, you know, that far away towards the end of this century?
So there we are.
That would be our kids. They'd be about 80. And they're doing the same thing that old people do today. But you know, something that I wanted to talk about really here was what are driving forces behind this? And so we're going to be talking a lot about driving forces. This is a driving force in memories. This is something that has been going on for a long time. If you look across the bottom of this chart, you'll see that it's got process geometries, and it goes kind of backwards. You know, the smaller process geometries are off to your right-hand side. And cost per gigabyte, which is on that log scale on the vertical axis, that represents what the cost per gigabyte would be for flash memory, which is the red line, and for some alternative memory, which is the black line. This is the thing that's been driving investment in alternative memory technologies, or now they're called emerging memory technologies, for the past 30 years or so, is that people have seen that there's going to be a crossing between these two lines. You'll notice the red line goes down. That's according to Moore's law. That's what is the cost to manufacture a byte of flash memory. And you'll notice that all of a sudden it just stops going down. It just kind of goes level. And that's where you reach what's called the scaling limit. For years, people have known that DRAM and NAND flash, or actually it was just flash in general, were going to hit a scaling limit. In the 1990s, I hired a guy from Intel who was hired into Intel, into the flash memory group from Western Digital in the 1980s, because Intel knew that disk was going to do something like this and that NOR flash was going to take over the world. That didn't happen, but you know, there have been a lot of junctures where people think this is going to happen. 3D NAND right now is because planar NAND has hit a scaling limit, and so 3D NAND was a way of working around it. But these other memory technologies, the thing that they've got going against them, and I'll talk about this a little bit more later on, is that it costs more to process a wafer. And so because of that, you've got the black line higher than the red line on the chart. That shows that you've got a higher cost per gigabyte, which is what's keeping these memories from actually taking over the rest of the market. They're too expensive. But once they get to a point where they can scale past NAND flash, and I'm sorry, I didn't put that down. So when scaling stops, then the costs stagnate. Anytime that the higher price technology can scale past NAND and can get to smaller, or past an entrenched technology and get to a smaller process geometry, then that's going to allow it to get to a lower cost, and cost is everything when it comes to memories. And so that's why people have been investing in MRAM, resistive RAM, ferroelectrics, any carbon nanotubes, any of those things. And the thing is that the scaling limit has been on us for years. The first time I heard about scaling limits was probably 1980, maybe 1981, when there were worries that we weren't going to be able to get past 7 nanometers. 7 microns. Today, everybody's very easily talking about 7 nanometers and how we're going to be able to do that. This is 1,000 times smaller. So, you know, you've got the new memories. Their intent is to extend scaling to keep us on Moore's law. And the technologies we have today, flash and DRAM, can't scale. The new technologies all can scale past flash and DRAM. You know, I say they can't scale. Flash has gone off to 3D, and so that's going to go for a while. DRAM, they keep finding new ways to do it because everybody in this valley is a super genius and seems to be able to just figure out ways to do it. But all of these other technologies have been sitting there just waiting for their opportunity to come in. There's resistive RAM, MRAM, PCM, ferroelectric memories, conductive bridge RAMs, and NRAM is carbon nanotubes. But there's something else that people haven't really talked about with these new memories, and that is that they're non-volatile. And so that's why there's so much work right now going on in SNIA for persistent memory, is because it's out there. You know, it's really going to happen. But also, something really nasty about today's non-volatile memories, NAND flash, is that you have to do block erases and page writes, and so you can't modify individual bits. You also have to pre-erase them. So, you know, these new memories don't need either one of those things. They're also significantly faster than flash. Flash has a certain thing that it has to do, part of the erase in the program mechanism, which just can't be sped up over time. And then finally, because of the fact that they've got no refresh like DRAM has, then they're lower power, and so they look like a good candidate to replace DRAM. And then, as that prior slide showed, if we get the scaling right and everything else hits a wall, then we'll be able to get these memories for cheaper. So they're all really wonderful things. And that's what's brought us storage class memory. The idea of storage class memory was actually conceived at IBM probably about 15 years ago. They said, all these things have been being developed for a long time. How are they going to impact computer architecture? And so IBM's been thinking for a very long time about how can they develop software that will take advantage of this in the future. IBM actually put together a definition, which I'm going to painstakingly read to you. So storage class memory combines the benefits of solid-state memory, such as high performance and robustness, with the archival capabilities and low cost of conventional hard disk magnetic storage. Now, if we pull that apart, there are actually only 4 statements in there. The first one is that it has to be high performance. It's got to be memory. It can't be storage. So NAND flash doesn't do that. It's got to have archival capabilities. Maybe I'm reading this too loosely, but I say that just means persistence. But what we seem to be ready to abandon with what we're doing right now is we're getting rid of the robustness of hard drives. We're okay with things that don't wear quite as well as a hard drive does. And we're also not looking for things that cost as little as a hard drive does, because we've found out since that time that there are ways to fit things into the memory storage hierarchy that are more expensive than a hard disk drive. Well, you know, you look at that, you say, that kind of looks familiar if you're as old as I am, you know, somebody with gray hair, because that's just core memory. So I'll pass it over to Tom, and he can talk a little bit more about that.
Thank you much, Jim.
You get to wander the stage. You've got the remote.
I do have the remote, yes. Amazing power. So I've had the honor of being a member of the IEEE, doing some things in it, among which is being participant in the IEEE Future Directions Committee under technical activities. And one of the activities they've had going on the last few years is the Rebooting Computing Initiative. Now, IEEE is the largest technical organization in the world, and they've got a lot of different disciplines involved, a lot of societies and things. I'll show you people that are involved in this. But the whole idea here was, as Moore's law, the traditional scaling algorithms we've been using, scaling rates we've been using in order to advance semiconductor technology slows down, we've got to rethink what are our approaches to be able to handle the huge amounts of data that we're going to have to process. You know, some of the pundits have said 163 zettabytes of data created per year by 2025. That's the latest IDC thing. So how are we going to use that data? How are we going to understand it? So we've got to rethink everything. And we have to go back all the way, looking back even to the roots of computing, back to Turing and von Neumann. Okay? And IEEE is kind of a natural one. And the reason why is because the whole computing stack, all the different things that are involved in computing, from devices through the compute architecture into the software, are part of IEEE. So here's an example of the societies that have been involved in this Rebooting Computing initiative: solid-state circuits, computers, circuits and systems, nanotechnology, Council on Superconductivity, Electron Devices, Society of Reliability, Council on Electronic Design Automation, IEEE Magnetics, among other groups have been involved in this. So, and the slides here I'm going to show, by the way, are from Tom Conte, who is the co-chair of the IEEE Rebooting Computing Initiative, and also a professor at Georgia Tech and a former president of the Computer Society. So we're going to take a look. This is this look from this rebooting computing, sort of a give an idea, a context for how memory and storage is going to fit into future computing architectures, which are going to drive consumer electronics, client devices, and enterprise in the future. And we're going to look at the different applications. We're going to, first of all, look at the whole computing stack. I'm going to show you that in just a minute here. In fact, that's it there. Going all the way from the bottom, we have the device level into the general computer hardware architectures, then up into the software at the top of it here. And we're going to look at different approaches and a few different approaches, and look at the level of disruption of this computing stack that each of these approaches would entail. And so at the legend here at the bottom, we see, it's down at the bottom there for those you may not be able to see it very well, going from a light color, the white color, to a deeper red. There's a more and more level of disruption as we move from the light to that red color. So we're going to take a look at first what's called Moore's More, okay? And as you can see here, we're going to have a lot of disruption that occurs in this, but it's basically going to be at the device level. at the storage memory device level, it's not going to impact so much the general computer architectures. It's not going to impact the way that we do algorithms to process information. Okay, and let's. And the other one is what we call hidden changes. Okay, now hidden changes where it starts to move up into the hardware stack, higher up the hardware stack of computers, but it doesn't impact the software very much yet. Okay, so there's very little disruption on the upper level of the compute stack. The next one, this third level, is where we're calling architectural changes, where we're actually starting to impact the whole computer stack, particularly on the lower levels, but also having some impact now on going all the way up into the software. And then finally, this fourth level, which is a non-von Neumann computer architecture. In other words, we're not doing anything like we've ever done it before, for decades now. So we have to rethink everything. So these are these four different levels of disruptive approaches that we're going to go through. And we'll tie that back into why that's important in terms of storage and memory. First of all, let's look at more is more. More and more, more. Okay, so more and more, it's the traditional continue the scaling as far as we can go, maybe 7 nanometers now, with those big FinFETs, 3D NAND, so we move into 3D stacked architecture, which can probably go to hundreds of layers potentially. New switches, unreliable switches, pre-threshold or close to threshold type logic devices, and into non-silicon type devices, some of which the people are out here in the exhibits here, things like MRAM, okay, where we're actually using the spin of electrons in order to be able to store information, potentially even in the future, perhaps even to process information, but that's part of these higher level architectures. Phase change memories, where we're using physical change in the state of a solid state device in order to change the resistance of that device and therefore be a memory device. Memristors and various types of resistive RAM devices where we're causing a change in resistance to be a form of memory, and then things like ferroelectric memory and different devices like that. So we're at the device level. We're changing what we're doing it with. We're not changing what we're doing yet. Okay, so that's this more is more approach. Let's look at this next level, what we're calling hidden changes. Now again, in hidden changes, we're starting to impact some of the lower levels of the computer stack. But they don't change the instruction set yet. They don't change the instruction set, and therefore they don't also have a huge impact on the software, how we're doing the software yet. So their devices there, for instance, include changes in the devices, include some logic level changes in functional units, in the microarchitecture of these devices. Context switch issue fits in here, and Jim will be talking about that a little bit later on. Microarchitectural support for non-deterministic logic devices, things like adiabatic computing or approximate computing technologies, things like that. But there's no significant impact on basically what memory and storage is necessarily, except for the device level. Next, we're getting into this architectural changes. So now we're getting into further levels of disruption. Sorry, maybe it's destruction. Yes, that will start to impact the whole architecture to some extent of computing. Now, these architectural changes beyond x86 type computing, examples of this are things we're moving into special purpose computing devices, which actually have to have some changes in the software, like CUDA with GPUs, FPGAs, things of that sort. So it's things, this is again where we're getting into the whole memory approach, moving computation to the data. In fact, at an event associated with the Mobile World Congress up in San Francisco yesterday, it was interesting, there was some speculation, Micron folks who were talking to, that actually the energy used to move the data around, to bring it to computers, is a significant component in the total energy budget. Something that, if we could change that, we could change, the power budget that we have in a lot of devices and make, for instance, these mobile devices last a lot longer. So in-memory computing, in situ processing examples, special purpose computing like the GPUs used for image processing, also now being repurposed for artificial intelligence and other capabilities, but it requires some new programming in order to program these special processors for these special applications. Now the final level is where we're going beyond von Neumann, beyond the computer architectures we've used since virtually the beginning of computing. These involve things like quantum computing. We're using things called qubits, for instance, to process information, and it's more than just single, 1 zeros. that you can do very complex processing. In fact, this stuff is so new that the IEEE standards group, activity last week said that they formed a group to define terminology around quantum computing. Things like neuromorphic computing. We're trying to create computing that emulates the way that our brains work to process information. Our brains actually do an awful lot for rather a low amount of power. It's something that our current processing capabilities aren't able to do, and we can do interesting cognitive and contextual things that modern machines can't do yet. Return of some kind of analog computing technologies. Now, all these are very exciting things. There's a lot of investment. There's startups involved in this. There's big companies putting research into this, but it's also very immature, and it's probably going to be a bit further away before we see these huge architectural changes, and they will take a while in order to create. Now, in addition to these changes in computing, we've got huge amounts of data we're going to be generating for various things. You know, we're from going to 4K, 8K video, to genomic research, big science, to future medicine, things of that sort. All the Internet of Things related activities, voice image recognition, autonomous vehicles, cybersecurity, industrial automation. There's a whole level of stuff that's going to drive that. Those estimates of like 163 zettabytes of data created per year by 2025. You know, we're going to have the means of processing this stuff, of running sophisticated algorithms, for instance, those often called artificial intelligence, in order to be able to make meaning out of all of this unstructured data, this data that you have to pull references out of the data itself in order to understand it, in order to be able to use it. So this stuff is going to require changes in our storage and memory, and so I'm going to turn it back to Jim, who's going to talk a bit more about that.
Yeah, there's one of those things that isn't going to go away is your jobs, I guess, too.
Good to know.
There are two major problem areas in memory today, and that is that memory loses its data and that storage is slow. And I'm going to address these actually in the reverse order which they've got. But, you know, that's the whole virtual memory system, caching, tiering, all of that is worked around these. So what do you do about latency? And there is a lot of talk today about moving compute close to the data. And then the other is to use lower latency storage. I'll get into some detail on these in a bit. But then, you know, what do you do about the non-volatility? The old way was just to make a number of verified copies to storage. And so hopefully you had fast storage, because every time you went out to put something onto storage, then you'd end up incurring a huge penalty with hard drives and a lesser penalty with solid state drives, but it's still slow. The new way that SNIA is doing an awful lot of championing on today is to make the memory persistent. Used to be that there were systems that you could buy that were just wretchedly expensive, that were just big DRAMs with car batteries in them. And you know, those worked for a while, but then around 2009, then people started putting together NVDIMMs with flash backups. And now we've got these new persistent memory or storage class memories that I was talking about earlier. That, you know, those are moving in there. And so with each one of these, you get not only higher speed, but also better economics. The persistent memory is a good solution to this thing. It's going to come to you in the form of an NVDIMM, and Intel is already beating on the drum for this with their Optane initiative using a 3D cross-point memory. But the other emerging memories are also going to get in there. Intel is just motivated to make this happen because they believe that it's an important part to realizing the full speed of the processors that they have. And so they're using this as a way of enabling the ecosystem to make their processors sell better. But there are some issues that come up that we're going to talk about, and that is context switches, cost, maturity, and software support. SNIA will be very big into that last. But today we've got NVDIMMs, which are serving as a very useful platform for prototyping for all of this. Your NVDIMMs, NVDIMM-N is what I'm showing here, and I think this is an a Giga one. This actually has the DRAMs on the one side of the module, and that's the side that's kind of below. So there are 8 DRAM chips on that. And then the other side has a NAND flash chip, because NAND is a denser chip than DRAM is, so you can get more bits into this fewer number of packages. and then a microcontroller that shuffles everything around. What I don't show with this is the supercapacitor that's needed to keep the DRAM alive during the time that you're moving the data around. But also, we're going to be moving to persistent memory technologies. And this is just kind of a further illustration of something that I said before, and I'm not going to walk you through all the details of this, but instead just you look across the top. That's all of current memory technologies. You look down the left-hand side, it shows you a lot of attributes to those technologies, whether it's volatile, what kind of power it consumes. And then I've done just kind of a good, bad, and so-so marking of these things with greens and reds. The real thing, the takeaway from this is to look at all these current memories and say how much red is on there. Some of them are too expensive, so they're red along the bottom. Some of them are volatile, SRAM and DRAM. So up in the corner, you've got these red boxes up there. But all of them seem to have some kind of a blemish. You go to the new memories, and all of a sudden, there's a whole lot of green. And that's because they're fast, they're non-volatile, they don't consume an awful lot of power. They are just all sweetness and light until you get down to the bottom line. And then it's, what is the cost? And today, the cost for these is very high. And it's going to take a lot of volume to move through the machine to make the costs of these go down. And so that's the thing that's really been standing in their way. Also, that scaling limit thing that I showed in the very first graphic slide, that also explains, a lot that way. So we've got that working, but then we've got another solution that people are talking about an awful lot, and that's bringing compute to storage. So in situ processing, we've got these things that happened in the past. Kinetic and the WD Labs microserver were early trials for this, but also we've got some companies today, NGD, NVXL, and ScaleFlux, and I noticed Thad Omura from ScaleFlux is here today. So they're all working to put together SSDs that have good processing inside, and that's something for those of you who listened to the Microsoft talk yesterday morning, you would have heard an awful lot about the benefits of that, but there was also some talk in the, I'm trying to remember the name of the company that presented with Xilinx, Missing Link Electronics, MLE. Yeah, and they were also talking about how embedding processing in there. This is the next thing. Today we're talking about persistent memory. Tomorrow we'll be talking about in situ processing. But there are also places where that's being done not in the storage. And so I've got compute in memory. A couple of examples of that are the Tommy processor and the Automata processor. And I'll talk a little bit about why that's failed, because it might draw a parallel to some of the stuff that's gone in here. And then we have a similar thing that was tried a while ago, and it seemed like those didn't work, and I'm not positive as to why, and that is these things from Schooner, Virid, and Violin. So I'll talk a bit about those. First of all, though, in situ processing, I thought this was a nice slide that Intel showed way back in 2013, I think it was. I'm sorry, Micron.
Yes.
Shame on me. The reason I said that was because it was Ed Dollar who defected from Intel and went to Micron, and I still have it stuck in my mind that he's Intel. He's not even at Micron any longer. But he did this really cool presentation at the Flash Memory Summit where Micron had taken standard SSDs and had reprogrammed the processor inside and stuck a little tiny piece of MySQL into the SSD. And they were able to get something where the processing speed of the system scaled directly in proportion, this blue line, directly in proportion to the number of SSDs you added to the systems. If you wanted it to run 8 times as fast, you just added 8 SSDs. And the server that was running all these things rarely had anything to do because the SSDs were doing most of the sorts. Whereas that green line represents what would happen if you kept adding SSDs to a server. The first SSD would just saturate the server's ability to do MySQL, and then you add SSDs and it doesn't really bring any performance increase. So, that was a real eye-opener for me. But then you've got compute and memory. And I have to admit, I put this one on first because it's an old college friend of mine, Russell Fish, has his own company. that puts together, it's put together an architecture of a DRAM with a processor in it. But they're not the only ones. Micron, once again, put together something called the automata processor. And that processor is designed also with, or that is actually a DRAM that's designed with a processor inside. And these have been designed to take advantage of incredible bandwidth that is available inside the DRAM chip, where all of the data is moving around in 4,000-bit wide or 8,000-bit wide buses. And it's able to solve certain problems that really drive people nuts. This is a nasty-looking diagram of network traffic that was something that was very easy to solve using the automata processor, but was something that would have been very difficult to do on a conventional server. So I think I hand it to you from here.
I think so.
Yeah. So.
Oh, no, we got appliances.
Oh, yeah, I forgot about that.
Well, they're coming up.
I was going to do. Yeah, okay. So these are the appliances that I promised to talk about a couple of slides ago. So Schooner Information System, which was later bought by SanDisk, they came out with something that was a box full of flash that would perform MySQL natively, and you'd just hand it commands and it would run on its own database. And it also it could be programmed to do a memcached appliance. It came with both of those in there. At about the same time, Virident came out with something that was very much like that. Virident was later bought by HGST. So, those were two examples of places where companies tried bringing out dedicated appliances, which kind of do the same thing as these memories and the in-situ processes. There was another one, Violin Memory, that came out with a Microsoft Windows server that was in there. Now, neither the DRAM chips with the processor in them nor these have fared very well. I know with the DRAM that has the thing inside that it goes against something the DRAM manufacturers thrive at, and that is they crank out tens of millions or hundreds of millions of identical chips without any variation in their factories. Once you ask them to make 1,000 of something, then the cost goes up by several orders of magnitude. And so that's something that has worked very much against them. I can't say that that's the same thing that caused the failure of these systems like the Violin, Virident, or Schooner systems, but it's perhaps some similar kind of an economic thing.
So if we're going to be carrying on this kind of integration, of storage and memory, storage and memory, but also trying to get the processing closer to the actual data. There's a lot of things that are required throughout the system, software support, changes in BIOS, CPU, perhaps even new pins in the bus. And one thing there's been stuff that's been going on in SNIA, especially the Solid State Storage Initiative, which, by the way, I took a look. It was founded in 2008, so next year, speaking of anniversaries, this will be the 10th, next year will be the 10th anniversary in September of the Solid State Storage Initiative. And so I've had a pleasure of being part of that group since it was founded. And we're moving, as we take a look at moving away from non-volatile memory, it has more and more characteristics of storage. We can start to treat things where we have used storage before, instead take a memory-centric approach to it. We can store, for instance, at the byte level versus at the block. We can avoid the traditional storage stacks. We can avoid things like flash translation because we don't have to translate. We can just deal with the native characteristics of flash and not have it act like a hard disk drive. So there's important things this allows, and the SNIA Solid State Storage Initiative has had this model of this programming model for this, where they're basically looking at, we have these persistent memory devices at the bottom here. We've got drivers that can operate and allow us to file system access this or kernel. But what really is sort of the holy grail eventually is where we show the application, instead of going through, say, a file system, where it can directly access the memory, the way that it happens inside the processor itself, where a lot of the working memory, working storage effectively is memory and acts like memory. And so that's where you have that direct interaction between the application and the persistent memory. And that's where we're going to be, a lot of things are going to be heading to in the next few years. So in order to do this, this is yours again. I think. Well, I'll do this. So again, we need BIOS support. Current BIOS, DRAM can corrupt at boot. What do we do when, you know, your data doesn't go away at boot? You want to do it? Okay.
Yeah. So Tom talked about the software needs to support persistent memory, but there are other needs. There are also BIOS needs, and there are also processor needs. And so what we have here is a list of how the way the current BIOS looks at memory and the way that the persistent memory BIOS needs to look at the memory. That the current BIOS says DRAM's corrupt at power on. The permanent memory BIOS says has to understand whether or not the DRAM's got valid data in it at power on, because it could be valid, it might not be valid, so there has to be a protocol for that. Power fail in current BIOS, you just say, okay, that's it, game's up. You know, the memory's gone, the register's gone, the cache is gone. With the permanent memory BIOS, everything has been pushed into the DRAM. The memory buffers have been moved in there. The memory itself is moved in. The registers are pushed in if there's enough power in the system to do that. And maybe even the dirty lines of the cache. There are ways of doing that. And so, you know, that's all stuff that has to be managed at the BIOS level. And that's something that the people who have been doing persistent memory have been working with software companies with for a long time. But also, persistent memory needs processor support. So we've got the software support Tom talked about, the BIOS support, the processor support. Intel has put new instructions in their architecture that they just announced about a year ago, where there's a cache and write, well, cache flushes are handled separately, but there's a write buffer flush command, where when that command is invoked, then anything that is waiting to be written is pushed into the memory so that it can be taken into persistent memory. But also, and I'm not sure that I understand the architecture well enough to know why this is important, they decided that rather than wait for a power failure to move the NVDIMM data from the DRAM into the flash memory, they instead just, they have an instruction that tells the NVDIMM to do that. But then you've got this other issue that's a context switch issue that is another place where the processor needs to take care of this. And I just prettied up a diagram that Doug Voigt put together, I think it was him, that shows how the speed of different technologies, storage technologies, works with the latency of there. And so with hard drives, SATA SSDs, and NVMe flash, all of those are things that can be satisfied through an interrupt-driven architecture. And so that's what that big blue box at the top is. It's okay to do interrupts. Then you've got a zone that is kind of, you don't know whether it's faster to do an interrupt because an interrupt takes a long time to do the context switch, or whether you'd rather just have the processor go into an idle loop and pull a flag. And persistent memory, unfortunately, largely falls into that questionable area. And so maybe the processor is going to have to change so that those context switches happen faster, or maybe software is just going to have to be written to pull the persistent memory. So it's back to you.
It is, and I'll do the final stretch here. So, but this is similar to the advent of SSDs. New software is required. We had to get in new ways, approaches for caching and tiering. It was part of what led to software-defined storage activities, particularly where we're integrating flash as the primary storage, faster I/O stacks, new hardware, and interfaces as well, including the NVMe and now potentially even NVMe over fabrics. So we'll need, we'll need similar efforts in order to make these things happen, to develop this in situ or memory-centric computing. And we'll have to do that to make this work with compute and memory virtualization, future approaches for virtualization where we have lower latencies to deal with. Could be really interesting. So in summary, there's a lot of things that are going to change. There's huge demand to be able to process mountains of data. And we're going to need new computer architectures and memory technologies, especially persistent memory technologies, that are going to be able to support this. We're going to need to bring processing to the storage in order to save power, in order to save time. We're going to have new approaches to computing the way we do things, which ultimately could change the very structure of programming and of compute. So we'll have to have support in software, architecture, and hardware. And so I hope you've enjoyed this. If you want to hear more about storage for unstructured data after you've gotten done here with the Storage Developers Conference, Jim and I are both going to be involved in this Storage Visions Conference in October 16th here. So with that, we want to thank you very much. I don't think there's time for questions, but we'll be around if you want to ask us some things later. Thanks.
I'm going to leave you with a blank screen here.
So folks, we're up against a 15-minute break here. The next session should start at 10:40, so enjoy your coffee. So thank you and welcome back from break, everybody. Our next presenter is Sage Weil. Sage is the founder and chief architect of Ceph, a distributed storage platform. He was also the creator of WebRing, a co-founder of the Los Angeles-based hosting company DreamHosts, and the founder and CTO of InkTank. Sage now works for Red Hat as the chief architect of the Ceph project. Sage.
Thank you. Can everyone hear me okay? All right, my name is Ceph, and my name is Sage. I work for Red Hat. I'm working on Ceph. Today I'm going to talk about a new storage backend that we wrote for Ceph over the past couple of years. This is a longer talk that's been adapted down to be shorter, so there might be some extra detail in the slides, but I'll hopefully it'll work out okay. Can't hear you. Louder, okay. All right. Let's see how this goes. All right. Let's see if the slides this works. And this doesn't work. And that doesn't work. Okay, so a bit of an outline about what I'm going to talk about. I'll give a little bit of background about Ceph, what it is and how it works, and what the backend actually is. I'm going to talk about file store, which is our old backend based on a POSIX file system on XFS, and why that was problematic. I'll talk about BlueStore, the new backend, and why it's so much better. I'll show some performance numbers, talk about some challenges and our current status, and then I'll wrap up. So first, a little bit of motivation. Ceph is a distributed object, block, and file storage system all in one cluster. It's designed so that it scales out horizontally with no single points of failure. It's hardware agnostic. It runs on commodity hardware. It's meant to be self-managing wherever possible. And most importantly, it's completely free and open source software. Traditionally, we've always talked about Ceph as being a scalable, high-performance distributed file system, and we always talked about sort of the three goals being performance, reliability, and scalability. Turns out the performance has been sort of a bit of a challenge for much of that time, and much of that is due to this back end that I'm going to talk about today. We just released our latest version of Ceph, Luminous, a couple of weeks ago, and sort of the two key highline features are erasure coding support for the block, object, and file interfaces. Previously, we only had it for object. And the second sort of feature is BlueStore, which is this new backend. And the two go hand in hand, as I'll talk about. So Ceph is built upon a distributed object store called Rados, which sort of underpins the entire system. This is the part that makes sure that your data is spread across all of your storage devices. It makes sure that when something fails, you detect it, and you re-replicate the data, and you heal, and you do all that good stuff. And then on top of that sort of internal object storage interface, we build a number of different access interfaces. There's an S3 Swift gateway called Rados Gateway. There's RBD, which is a virtual disk block device that does snapshots and cloning and multi-site asynchronous replication and all that good stuff that you use for private clouds mostly. And then there's CephFS, which is a distributed POSIX file system. But all of those are layered on top of Rados, which is the bit that actually stores all of the data in the cluster. That Rados cluster is composed mostly of OSDs. These are object storage daemons that sit on a number of hosts. Typically, or traditionally, we would have an object storage daemon sitting on top of a local file system, XFS, and that would sit on top of your raw storage device, disk. In reality, it's a little bit more complicated than this. There's a bit of the OSD that's called file store, which is the module that's responsible for dealing with all that local storage on the local device. And so it hides all the details of how we're actually writing data into XFS. And it turns out that this has been sort of one of our key challenges in the past. And partly it's because of sort of the history that we took, the way that Ceph was designed and how we got to the current point. So in the beginning, we didn't actually use XFS at all, or a file system. We wrote a specialized file system called EBOS, an extent-based object file system. This was an entirely user-based file system that was optimized and designed specifically for storing objects with the workloads that we expected to see. So EBOS used a raw block device. It had a copy and write B tree, and it stored objects, which are sort of like files. And then it had a custom interface that it exposed to the rest of the Ceph OSD. And then we had a second implementation of this abstract interface called FakeStore that we used just for development. It would store objects as files, and we use it on our laptops when we were developing. But EBOS was sort of the thing that was meant to store all the data in Ceph. That interface we internally called Object Store. It was the sort of the internal storage interface for storing stuff locally on our locally attached storage device. And the interface is pretty simple. We had objects, which are sort of like files. It's just a lump of data. It's a bunch of bytes. You could associate some attributes with objects. So think small key value pairs like version equals 12. And later on, we added what we called OMAP, which was key value data. So we could store key value data inside an object as sort of this self-contained unit of data in the system. Collections were kind of like directories. It was just a bunch of objects that are grouped together. In reality, objects in Ceph exist in a logical storage pool that's spread across the entire cluster, and a collection was just a shard of that overall pool, a subset of a slice of the namespace. But one of the sort of the key features of this internal interface that evolved because we had control of that lower level object storage system and the thing that was above it, and it was internally transactional, we made that a rich interface so that all the update operations that the Ceph OSD was passing down to this internal module were in the form of transactions. So it would be things like update an object, update its version, and log something saying that we made that update, and that would all be committed atomically on disk. And we had that flexibility because we're building it all ourselves, and it was sort of the most natural thing to solve the problem at the time. Some time went on, and we started adding more things to eBOS. Eventually, we got to the point where we needed to add data checksumming on disk. And Btrfs arrived on the scene, which internally had a very, very similar design to what eBOS was doing. But it was in kernel, it had a whole community around it, it looked like it was going to be the future of Linux file systems. And so we said, hey, we should just use Btrfs, hook into their internal transactions, stop maintaining our own special thing that was just for Ceph, and we can save ourselves a bunch of time and effort and focus on the other parts of Ceph about replicating things across nodes and so on. So we did that for a while. It turns out that exposing POSIX transactions into user space just was a bad idea. You could give a whole talk about why that's the case, but trust me, it's a bad idea. Later, we pivoted to using XFS instead of Btrfs when we were finally rolling Ceph into production behind OpenStack clouds. So we sort of shifted back away from eBOS, leveraging POSIX file systems. And to do that, we took that fake store, that sort of toy implementation of the interface just for doing development, and we renamed it File Store, and we made it do all the things that it had to do. So it would store objects and files in POSIX. The collections became directories. So the kind of directory layout and structure on disk that you would expect. We added in LevelDB in order to store some additional metadata and to store that key value data that we have. It turns out that every single Linux file system has its own sort of unique special limits on the size of xadders and how many xadders you can cram into a single inode. And so we also have a bunch of hackery to sort of spill over large xadders into LevelDB when necessary. But overall, it kind of worked. But emphasis, I guess, is on kind of. So there are sort of a number of big challenges that came up when we were trying to sort of shoehorn our nice transactional interface that was natural for Ceph OSDs onto a POSIX file system. And the first one is transactions. We had a transactional interface. It made the rest of Ceph's design so much better and easier, but it didn't really map onto file systems. So most transactions in Ceph are pretty simple. It's something like write this little bit to a file, update the xadder on the file saying that the version is now n+1, and insert a log entry into the log saying I touched this this object. And those logs are important for doing recovery efficiently, so we know exactly what things have changed and which versions are where and so on. But transactions can actually be very complex, so that's just the simplest case. But doing that on POSIX doesn't really work. POSIX doesn't provide any kind of transactional interface, so we did sort of the simplest thing, which is basically just to take the entire transaction description, including the write and all the updates, serialize it into a bunch of bytes, write it to a write-ahead journal, commit that to disk, and then write it back to the file system. And that gave us the atomicity we needed so that if we crashed, we could always replay the journal, and we could always leave the store in a totally consistent state. But that means every write in Ceph was written twice. We wrote it to the journal, and then we wrote it to the file system. So that was inefficient. And also, it was just gross. There's some operations that are sort of non-idempotent, like things like rename that have a read side and a write side. And so there was a lot of ugly hacks to make sure that if you replayed this journal, you would always get the right result after the whole thing was replayed. So it was frustrating. The other challenge was the kernel cache. So in general, kernel caches are wonderful. File systems in Linux all share the page cache and inode cache. It's all magically managed for you. It'll use all the available memory in the system if it can. As soon as there's memory pressure, it'll sort of free things. It's great. You don't have to think about it. It's fast. It's very highly performant. The problem is that when you take that and you combine it with write-ahead logging, things suddenly suck again. So we do a lot of read, modify, write operations in Ceph where we look at the state, we make a change, and then we update it. But because writes have to go through a journal before they're applied to the file system, You literally have to wait for the previous transaction to commit, be applied to the file system before you can read its effects and prepare the next transaction and then write again. So you end up either serializing updates based on your journal and the number, however many IAPs you can get out of your slow hard disk, or you have to re-implement another sort of cache in your own that's just managing or keeping track of in-flight writes, so you avoid this sort of annoying serialization. So that was frustrating. But the last and probably one of the biggest problems is problems with enumeration. So the way that Ceph takes all of its objects and distributes them across the cluster is it hashes the name, and it sort of takes that 32-bit hash value, and that defines a well-defined sort order of all objects in the system, and it shards that namespace into pieces and distributes them to certain nodes. So when we do enumeration of the objects in Ceph for like scrubbing, for consistency checks, or enumerating objects in order to replicate them across to other nodes, we have to have this well-defined order for everything to work. But POSIX Reader does not give you ordered results. It's sort of randomly whatever the file system happens to implement with its internal hashing and B trees and whatever else. We also have this need to take an existing shard as the data set grows and split it into pieces, and so we can sort of redistribute it across the cluster. And when we're storing these groups in directories, we have to literally take a bunch of files and copy them to other directories in order to split them in pieces. And so POSIX didn't really give us the right tools for the job. In order to make this work, the file store backend would basically take all of the objects in a collection and it would hash directories based on that sort of a prefix of the hash. So as soon as a directory got bigger than some threshold, it would split it into pieces based on some hash prefix, and if the directories ever got small again, they would get sort of merged back into the parent. And then whenever we wanted to do enumeration, we can list all the files in a directory, which hopefully is bounded to be some small number, sort them in memory, and then give back an ordered result. So it worked, but it was gross, and you had all this extra directory renames. It sort of wreaked havoc on XFS's allocation group hints about trying to keep things in the same directory close to each other. It just messed everything up, and it was pretty slow. And the headaches sort of continued. So as you were populating a cluster and putting billions of objects into the cluster, all of the nodes in the cluster would sort of hit these split thresholds at the same time and start splitting directories into pieces, and throughput would totally tank as all of them did that at the same time. It turns out that we want consistent performance, and so when we're writing things into XFS, we want to bound the amount of sort of deferred write-back work that's going to happen. We can push things to disk with fsync, but we can't control the number of inodes that are sort of dirty in the XFS journal, and eventually those need to get written back to the XFS internal B trees, and we can't control when that happens or how many of them there are. Our QoS efforts were thwarted because we couldn't really control the depth of queues. And when we do snapshots in XFS, we have to clone objects. XFS didn't have an efficient clone operation, and so we'd literally be copying objects and have this sort of latency spike. We came to the realization that XFS was just the wrong tool for the job. We had a very different storage interface that we wanted to implement, and putting it on POSIX was not the right answer. And so a couple years ago, we sort of started experimenting with new custom backends. NewStore was an attempt to take just all the metadata about objects and put it in LevelDB, but still store the data in files. That helped, but still sort of ran afoul of some of the same issues in the POSIX interface. And eventually we said, forget this, we're going to write a completely fresh backend, again, sitting on a block device, and we called it BlueStore. So BlueStore is sort of a block version of NewStore, where we're consuming raw block devices. We leverage an existing key value database, RocksDB in our case, for storing the metadata, so we don't have to sort of rewrite everything from scratch. Data is written straight to the block device. We have pluggable inline compression, full data checksums. And the goal with this is to target sort of the current generation of devices. So hard disks, sort of regular SSDs, and NVMe devices that you have out in the wild today. The key challenge in this was how to figure out how to make BlueStore share the underlying block device with RocksDB. So RocksDB is a LSM tree key value database that's very popular, but it uses files to store all of its state. And we don't have a file system anymore. We're sitting directly on a block device. And so what we did is we created a custom backend for RocksDB called BlueFS. BlueFS is a super simple file system. And calling it a file system is generous because we implemented the bare minimum necessary to support just what RocksDB does. It turns out that the LevelDB and RocksDB developers did a really good thing in abstracting out all of the operating system dependencies. So all the file operations are already abstracted behind this env interface, and we just had to implement a class excuse me, And we could slot in all the write file operations to back RocksDB. So BlueFS is super simple. Its on-disk layout is super simple. We have a super block, and we have a journal. All the metadata lives in the journal. When we update things, we write it to the journal. When we mount, we just read the entire journal and read all the metadata into RAM. There's no other metadata structures on disk. And then when the journal gets too big, we just sort of rewrite a new journal that has just the metadata that's still accurate. So periodically we compact it. But it turns out that RocksDB writes big files, so we can keep everything in RAM. Periodically compacting it is like totally sufficient for our needs. The only sort of clever thing we did is we configured RocksDB so that it wrote different types of files into different quote-unquote directories. So its write-ahead log, its WAL files were in one directory, and its database files were in another. And then BlueFS would look at the file name, and it would map that data to different devices. So we could put the RocksDB journal on like a fast NVMe or NVDIMM or something like that, and the rest of the data would go on disk. But aside from that, BlueFS was like just as complicated as it needed to be. And that solved our problem. So a little bit about how BlueStore would store its metadata. I'm going to go through these pretty quickly because it's probably not super interesting about exactly how BlueStore works, but mostly that you can write something that's not too complicated to solve your problems. So the main metadata structure in BlueStore is an O-node. This is like an object or a file. It lives in a single key value pair in RocksDB. And it has just a little bit of metadata, how big the object is, what its attributes are, and information about how the extents are stored on disk. I'll talk about that in a moment. The collections, as I mentioned, are sort of this shard, a slice of the overall object namespace. But we constructed the key names for all of our objects so that they sort in the same order that they logically sort in Ceph. And so the collection is really just a description of what the current sharding is and which ranges are mapped to which shards. And so when we split, in order to do resharding and to redistribute data, all we do is we change that description, but we don't have to actually rewrite any other metadata because they're already sorted in order in the tree. So this gives us nice ordered enumeration and efficient splits. A blob is metadata about some data that's on disk. So it's which extents they're stored on the block device, all the checksums for that data on disk, and if it's compressed, information about the compression, the compressed size versus uncompressed size. Every once in a while, or sometimes objects get cloned in Ceph, and so there are actually multiple objects pointing to the same bytes on disk. In that case, we need some additional reference counts on those extents before we release them, and so there's also a shared blob structure that handles just the reference counts. And then the extent map is the bit that sort of glues together the objects and the blobs. So it's just mapping bytes in the object to which blobs and which bytes are sort of referenced by those objects. We normally sort of serialize it in chunks, so we have which extents and which blobs. If it's a small object, then we can cram it all into one key value pair and stick it right with the O-node in one slot in LevelDB or in RocksDB, so it's nice and efficient. But if you have a big object or an object that's fragmented or have lots of different small writes or something like that, then that might be a pretty big map. And so we shard it into pieces so that we can spread it across multiple key value pairs and limit the size of our updates and so on. And there are a few corner cases to deal with. If a sharding boundary crosses a blob, then we have to store the blob in a different place and some other details. But those are the basics. The data path also is relatively straightforward. So again, our interface is transactional, so we have information about what transactions are in flight. That's a trans context. And because we have sharded the namespace into collections, each collection has an independent sequence of transactions that are ordered within that collection, but not with respect to each other. So we have lots of parallel queues of events that are ordered, but no sharing between them. So BlueStore is free to sort of schedule things as it sees fit. And then when we write data, we do it in sort of a write anywhere, copy and write fashion. So if the write is large enough above our allocation size, we'll allocate new space on disk and just write it to new space. Once that commits, then we can write the metadata transaction that references it. In some cases, there's a blob that wasn't completely written. There are parts of it that sort of are still unused, and so we can write into an existing blob. It's an unused region, and there's no other references to this block, so we're not clobbering any existing data. But then the third case is when we have a small write that's sort of overwriting existing data. And in that case, we can't overwrite the existing data because if we crash at the wrong point, then we'll corrupt the previous state and not have committed the new state. And so in that case, we put the data that we're writing in the journal event. So the transaction says, this is the update, and this is the write that I'm going to do later. So it's like data equals journal in ext4 or something like that. And then after that commits, then we asynchronously apply that write to the system. Those are called deferred writes. We don't have a kernel file system anymore, so we have to implement our own cache. That was a bit more work, but it turns out to be better in the end. So we have cache nodes for each collection. They're all independent, so we don't have any false sharing. Blobs can have data buffers cached as well. We always have to track in-flight writes so that we can sort of read the effects before they commit. But we can also cache things on disk if we think we're going to read them again later. And then both the buffers and the nodes are linked to a structure that we call a cache. That's basically a big LRU so that we can handle cache trimming. We implemented a 2Q, actually, so it's resistant to invalidation due to a sweep. But the main sort of trick we did here is that we sharded the cache for parallelism. Ceph OSDs already have sharded work queues for all of their requests. So they allocate different placement groups to different queues so we can utilize multiple cores and they don't share between them. We mirror that exact same sharding scheme in BlueStore, and we match that with the caches so that the CPU, the cores already have an affinity to the cache structures, and we don't have cache lines ping-ponging between cores and so on. And that's sort of the BlueStore design in a nutshell. So did it all work? We'll look at some performance numbers here. These are, I apologize, some of these graphs are pretty old. They're from a talk I gave last spring. But they reflect sort of the same state of affairs. The only sort of confusing bit here is that this is showing FileStore, BlueStore, and a couple other development versions. The lines to pay attention to are the red line, which is the BlueStore, which most closely resembles what we have today. And confusingly, the blue line is FileStore, the old thing. So just keep that in mind. The top line, the top graph is throughput. So the first thing to notice here is that for large writes, when we're writing 4 megabytes at a time, we're basically essentially twice as fast as FileStore. And that's because we're avoiding this double write. We don't have to write the data to the journal and then apply it to the file system, but we can just write it straight to where it's going to go and update the metadata. On the bottom graph is the exact same data, but shown in terms of IOPS. So you can also see that for small writes, we're also about twice as fast. And that's just because we're avoiding all the machinery of the file system that's not quite adapted to what we want to do here. The interesting bit is that huge knee where it jumps up at between 32 and 64K, and that's because of the allocation size threshold. So writes at 64K or above, when we submit a write, it's just allocating a new extent on disk and writing it to a new spot on disk. And so when you have lots of writes coming in, it's just sort of streaming all these things out. It's nice and fast. Whereas once we drop below that threshold, it switches into the deferred write mode, where it's journaling the update into the journal and then asynchronously overwriting the existing data on disk. And this is really just a trade-off between performance and fragmentation in the future. So you can adjust that up and down. The main thing that we did after these tests were done is we changed the way that deferred writes were handled. So we batched them up in memory much better, and so that we can write them out more efficiently. So that line has moved up a bit. But that's where that comes from. Sequential writes are similar. Again, for large writes, it's indistinguishable for random writes, so it's much faster. On small writes, though, we had sort of an annoying, confusing result where we showed that we're actually much slower than FileStore for sequential writes. And it turns out that the reason was because of the way that these deferred writes are being handled. With FileStore, we would write them to the journal, and then we would write them to the file system. But XFS was allowed to sort of accumulate a lot of writes in cache before it actually wrote them out. And so it would batch them up and turn them a bunch of sequential writes into one big sequential I/O. Whereas this version of BlueStore was actually dispatching them as soon as they committed. So we had sequential I/Os, but they would be spaced apart in time and they'd be interleaved with journal updates, which is very inefficient. So the deferred write batching that I just talked about that we implemented since then has brought this line much higher and above where FileStore was. So that's hard drives and sort of normal I/O. It turns out that the way that BlueStore manages metadata also made a big difference on performance. So these tests were for the S3 interface, which is writing objects through the Rados gateway into Rados on top of a cluster with both hard disks and NVMEs for the journal and using erasure coding. The blue and red, the small bars are FileStore, and the yellow and green are for BlueStore. And the main thing to take away here is that we're anywhere from 2 times to 5 times as fast as file store. And that the amount of spread tends to vary based on the level of sharding between buckets. So the way that the Rados gateway works, it's maintaining an index for each bucket, each S3 bucket, so that you can do things like enumerating objects and applying quotas and so on. And it's a read, modify, write operation on those indexes. So depending on the level of sharding, you may or may not be bottlenecking on the updates, the serialized updates on those indexes with file store. And with BlueStore, we don't have this annoying issue where you have to wait for the write to commit before you can read the effects and do another read, modify, write. So we eliminated that problem, and life is much, much better. It turns out that sort of the other big feature in Ceph Luminous that I mentioned, these erasure code overwrites, also allowed us to do things that we couldn't really do before. So erasure code overwrites in general are hard because you have to do a 2-phase commit. You can't, you have to make sure that when you're overwriting part of a stripe, you either roll all the way forward or all the way back. Because if you have half the updates apply and then you crash, you sort of can't read the old data or the new data. That's why EC updates are hard in general. And so when we implemented this, the OSD basically is cloning the regions that we're about to overwrite with a temporary rollback object, so that if we somehow fail to proceed, we can always roll back. In BlueStore, it's all copy and write internally. You can do this very easily and naturally. But with FileStore, POSIX doesn't give us these sort of copy and write semantics. It literally has to read the data and write it to a temporary file and then overwrite the data to commit it. And so the performance is sort of predictably terrible. These graphs are comparing IOPS from a replicated pool versus a couple different erasure codes. So on the left side, you have BlueStore. So the EC overwrites are slower than replicas because there's additional overheads and we're doing this 2-phase commit and some extra work. But it's usable. But when you look at FileStore, it's like literally unusable because it's so slow. We just don't allow you basically to use this new feature if you're using the old backend. And part of the reason why we waited so long to implement these overwrites was because there wasn't really a good way to do them efficiently with the backend that we had on hand. Now that we've sort of reclaimed control of our entire storage stack and we can implement the functionality that we need for Ceph in the backend, then we can implement the features in the natural way and without sort of fighting with this impedance mismatch between what POSIX gives us and what Ceph needs. There's some other challenges that are worth mentioning. We moved all of our caching into user space. We can't just rely on all the magic stuff that the kernel is doing. So we had to do some extra work to make that work properly. One of those things was building a mempool infrastructure that allows us to easily account for allocations. So we can easily annotate types, like STL types in particular, in Ceph as being belonging to a particular mempool. And then we can look at how much memory is being allocated. And we can use this to basically control, to first of all observe how much memory we have consumed by our cache, and then control pruning of the cache based on actual memory that's being used. And as a bonus, we have some debug options that let us also tell which specific allocations are being done so we can tell what's going on. Sort of the big downside, though, is that suddenly the cache size is a configuration thing that the administrator has to decide. You have to actually tell the OSD how much memory it should consume for its cache. Before, the kernel would just magically use all memory, and now we have to decide how much we're going to use. So that's sort of the main gotcha. And as a bonus, we can finally have a sane implementation for some of the F-advised hints that we implement. The kernel never did and overuse properly, and sort of a pet peeve of mine, I can finally implement it properly. So that was a bonus. We also have to be very careful about how much memory we used. Previously, all of our allocations were sort of for in-flight IOs, and so it didn't really matter if they were efficient or not. Now we're using gigabytes of RAM, and we want to make sure that we fit as much useful metadata as possible. So we have to pay careful attention to struct packing and so on. Checksums are a little bit tricky. If we use sort of the default 4K granularity for checksums, it's a kilobyte of metadata for every megabyte on disk, which is kind of a lot. But it turns out that BlueStore is able to observe hints on the IOs that it's doing. So if it's Rados Gateway, for example, S3 objects being written that we know are going to be read and written sequentially, then we can do very large checksum blocks. So we can checksum a 128K block with only 4 bytes. And then you get much better metadata efficiently. The other thing we've had to pay attention to is just sort of naively using all of the data types at our disposal, like red-black trees. can wreak havoc on the CPU prefetching, and judicious replacement of some of these data types with in-memory B trees and so on has had a huge impact on the performance. So we spend a lot of time poring over perf results and so on to make sure that we're doing this efficiently. RocksDB has been sort of a boon and a bane. Mostly it works great and we don't have to think about it, which is awesome. But there are a few sort of issues that we have to pay attention to. Compaction, this background rewriting of the LSM tree SST files into new files. That impact can grow as the overall size of your metadata grows, so we have to keep an eye on that. There's some issues in RocksDB where it invalidates its own cache when it does a compaction that they haven't really addressed yet upstream. So we're sort of pushing them to do that. And also, when it is doing all this compaction stuff is sort of background work, but we don't have a good way to prioritize those IOs when we're actually submitting the kernel through the kernel AIO interface yet. So that's a bit frustrating. We also write a lot of keys that we write and then delete immediately, and RocksDB sort of doesn't realize that and can amplify those to other SSTs, so we're trying to fix that. We hid all of this behind a generic key value interface, so we could swap in a different key value database for RocksDB if we wanted to. But we're open to alternatives, but we haven't really found anything that's as good or better. So for now, we're using RocksDB, but we're hoping someday we'll have a better alternative. So current status, I mentioned that Ceph Luminous was just released a couple weeks ago with BlueStore as both the default and supported storage backend. All the existing clusters out there are still using FileStore, and so we have documented methods for basically converting those over to BlueStore. Mostly that just means leveraging the existing Ceph redundancy recovery stuff, so you provision a new BlueStore OSD and delete the FileStore one, and all the existing Ceph recovery stuff takes over. And there are some sequences to sort of make that efficient. Our current efforts on BlueStore are mostly around optimization, paying attention to how much CPU time we're spending, trying to optimize the code paths there. It's all sort of working and stable, but it's sort of still early days. This is our first real release, so we have a lot of work to do there. One of the more exciting things being worked on, mostly by the XSky guys, is support for SPDK, which is a kernel bypass library for NVMe. It cuts down the latency as far as bypassing the kernel AIO and some of those context switches, which is nice. But the other thing that SPDK offers is you can prioritize IOs that are being submitted to, which hopefully will help us solve some of the compaction issues. And we have a complete FS check that does a full consistency check, but we're sort of a limited set of inconsistencies that we can repair, so we're sort of making things more robust there. But we have to be careful because Ceph is a distributed system, and mostly if there's a failure, you want to use sort of the existing recovery mechanisms to deal with it. And if there is an inconsistency in an instance of BlueStore, we don't want to somehow let that repair it incorrectly and let that inconsistency get propagated to other nodes. So we have to be very careful that we understand when we're repairing something that we're actually making it better and not worse. So that's a challenge. Future work, we're talking about tiering, how we can combine hard disks and SSDs behind one BlueStore instance. Unclear whether we should try to implement that functionality within BlueStore or use existing tiering block devices like Bcache or DMCache and then hint RIO so that it can sort of do the right thing. Leaning towards hinting to the block layer so that we don't have to think about it. We've talked a lot about host-managed SMR and things we can do to BlueStore to make it work sort of natively on host-managed devices, but we'll see if that's actually worth pursuing. And then there's also sort of future technologies. So there's persistent memory 3D NAND coming. There are lots of NVMe spec changes with blob stores and key value stores, and so we're keeping an eye on those to figure out how we should best utilize those as we sort of move into the future. So in summary, Ceph is great at scaling out. XFS is great too, but they sort of weren't a match made in heaven, as it were. POSIX was just a poor choice for storing objects for Ceph. So our new BlueStore backend is so much better because it sort of behaves the way it's supposed to behave and we're not sort of fighting against the wrong interfaces. We find that designing our internal storage interfaces without sort of being biased by POSIX was a win. It took us a long time to sort of get here, but finally we can sort of use the interfaces that are natural for Ceph and also implement them the way they are naturally implemented, and we can sort of reap the benefits. But we're not done yet. We're still working on performance and other things. So thank you very much. This is a picture of the Ceph cluster in my basement. It's a combination of hard disks, SSDs, and NVMe's. It's running the latest Ceph with file system, cache tiering, erasure coding, and of course, BlueStore. And as a bonus, It can be administered with untrained IT staff. This is my youngest daughter here swapping an SSD in the cluster. So, thank you very much. I think we have just probably 1 minute for questions, if that.
Have you taken a look at NVMe I/O determinism and how that might fit in here and improve performance?
I don't think so. I'm not quite sure what you mean by I/O determinism, but yeah, we've done a fair bit of testing on NVMe, but mostly we're bottlenecked on CPU and other parts of Ceph. So the good news is that BlueStar is fast enough that it's not the slowest part. The bad news is that we have more work to do. So.
Hello. Is the memory consumed the problem? You mean all the metadata is stored in the memory?
It isn't a problem, no. So BlueFS, the backing for RocksDB, loads all its metadata into RAM, but it's a very small amount because it's just information about the RocksDB files, so it's a small amount of RAM. The BlueStore cache that's caching the metadata for all the objects that BlueStore stores is sized however you want it to be. So you decide whether it's 500 megs or 3 gigs, and it'll appropriately cache as much metadata as it can or not. So, yeah.
What specifically led you to evolve from LevelDB to Rocks?
It was mostly just sort of seat of our pants. RocksDB had an active community around it. Lots of people were working on it. Actively developed, whereas LevelDB is kind of deadish, it seemed. So we wanted a responsive upstream so that when we had changes and improvements, we could have them be picked up.
Does the BlueFS support the snapshot by itself?
Does BlueFS support snapshots? No, because BlueFS is just for backing RocksDB, and so it's just writing sequential files, reading random files. There's no rename. There's delete. That's about it. Like, it's just enough to run RocksDB and nothing more. Yeah.
Yeah, you mentioned about the OSD level, block level, and file level granularity for ratio codes.
Mm-hmm.
Do you also have anything much more granular, like chunk level?
Yeah, so all of those, the object block file interfaces are all built on top of Rados, and Rados has a set of primitive operations that support snapshotting. And it's actually on a per object granularity. So how you sort of expose that and package it up in a nice way depends on the pieces that sit on top. So RBD does it on a per image, per volume, virtual disk. CephFS does it on a directory basis. You can snapshot directories. Yeah.
Thank you.
All right, thank you very much.
So our next speaker is Martin Peterson from Oracle. Martin Peterson has contributed. Okay, great. So our next speaker is Martin Peterson with Oracle. Martin has contributed to the Linux kernel since the early 90s. As Linux storage architect at Oracle, he focuses on future I/O and storage technologies. Martin also participates in various industry standardization efforts and co-maintains the Linux SCSI stack.
Thank you. All right. All right, good morning, everyone. So I was asked to give a little bit of feedback here. I was asked to give an overview of what we're doing in Linux, and Linux from a storage perspective. And Linux is pretty big. We have thousands of developers contributing, and I don't think anybody individually is on top of what everybody else is doing. So I had to look at numbers to actually get a good idea what to talk about. And so here's a graph of the last 5 years of development activity. I'm counting commits, so the commits could be small or big. But fundamentally, you can see we have things broken up by subsystem here. We have IDE, SATA, SCSI, the core of SCSI, like basic functionality, not device drivers. NVMe, the block I/O layer, and persistent memory as a new thing. We don't really know whether it's storage or memory yet. Sometimes it's both. So we're not sure where it lands, but I included it here because there's a lot of activity going on in the area. Anyway, we have a lot of SCSI drivers. We have a lot of SCSI drivers. I mean, maybe if somebody had one, we would in theory still support an ST01 or something like that. So we have a lot of drivers. So I had to filter out all the SCSI drivers from these graphs to get a little bit of a clearer picture of what was going on. So you can see here we have the individual I/O subsystems in the kernel. IDE is our old Linux IDE stack for parallel ATA and that kind of thing. And as you can see, this is the red graph down here. There's nothing going on. It's been in maintenance mode for a while. We would really like to get rid of it. We have one maintainer that is objecting to us just throwing it away for fear of reducing and introducing regressions on his favorite legacy hardware. So it's still sitting there, but we'd really like to get rid of it. As far as SATA is concerned, you can see we're around 200 commits per year, give or take, in the SATA subsystem, sloping slightly downwards. There's not too much new stuff going on, and we'll add workarounds for devices that are misbehaving and add new PCI IDs when somebody introduces a new HCI control and that kind of thing. But fundamentally, there's not a lot of new development going on. As a matter of fact, the two only new things that have been going on in the scope of ATA are support for OPAL, encrypted drives, and support for zone drives. So I'll get back to those two later. As far as the SCSI core is concerned, you can see it's on a path that's very similar to the path NVMe is taking. And there's actually a reason for that. And that is that in Linux, unlike other operating systems where read and write operations are sort of abstracted and provided by the OS, but pretty much everything else you want to do to the storage involves a pass-through operation of some sort to cause a cache flush or something like that. In Linux, we have a pretty rich block layer arbitrating between what the applications and the file systems see and how operations are actually physically translated into something that makes sense for the hardware. So a file system can do a flush, and that will get translated into something that makes sense depending on whether it's an NVMe device or SATA or SCSI or whatever. So NVMe and SCSI are often following the same path because what we're doing is we're adding support for something in the block layer, that's the black line. We are adding a primitive, some sort of operation at the block level, and then we're implementing support for that particular feature in both NVMe and SCSI at the same time. So you can see that the block layer here has been pretty steady for a while. Over there on the left side in 2013-14, we implemented support for block MQ. I'm going to talk a little bit about that. That was a bit of a bump after the block layer had been a very flat line for about a decade. Nothing really was changing at the block layer between early 2000s and until we introduced block MQ. So things tapered off slightly, and then the last year, things have been going crazy. And I'm going to talk a little about what all that crazy stuff is. So the problem we had with the original block I/O layer, which was essentially a revised version of the way back time, like 90s block layer, it got redesigned in 2000s for what was modern hardware at the time. But fundamentally, the I/O path was single-threaded. And there was a big fat lock on every queue, so only one application could submit I/O to any device at any given point in time. And with the advent of PCIe flash devices, this predates NVMe slightly, but there were several proprietary PCI flash controllers and so on, several devices that started having support for multiple submission queues. So we needed to do something pretty drastic to the I/O path to accommodate these devices. And the net result was a rewrite. Matthias, who's sitting down here, was actually instrumental in doing a lot of this work to add support for multi-queue devices. One of the benefits is that from an application perspective, the submission is lockless. Regardless of what the capabilities of the hardware is, the applications per core are submitting into a software submission queue, and then that queue then gets demultiplexed into whatever the capabilities of the hardware has. So if you have a device that only has a single submission queue, which is actually the case for a lot of devices out there, most of the SCSI controllers we have in the kernel have a single submission queue. They may support multiple completion queues through MSIX and whatnot, but the submission queue into the actual controller ASIC is single queue. But applications still get the benefit of the lockless submission. So on average, the application spends less time waiting to submit the I/O than it did in the old days when it actually had to wait for the queue lock to be free. So the new block I/O layer, BlockMQ, is mainly used by NVMe and SCSI. Another problem with the old I/O path is it was heavily optimized for slow media. It was optimized to reduce seeks and to merge I/Os and coalesce I/Os because devices typically had very low queue depths. So there was a win in merging adjacent I/Os together, so you would only use one I/O queue slot. The HBAs had limited queue contexts, and the devices themselves had a pretty shallow queue depth. So the core of the old block I/O stack was to try and reduce seeks and coalesce I/Os as much as possible, and we had a wide range of I/O schedulers in place that allowed us to, depending on the workload, do the right thing. BlockMQ was completely in the opposite corner, in the sense that the whole point was to be lean and mean, reduce all the fat, and not have any of all this stuff in the way. The I/O path needed to be as short as possible because we've moved from a universe where all that mattered was throughput to a universe where latency really is the only thing that applications care about. You know, it doesn't matter how long time it takes to write the whole thing as long as the response is really quick. So BlockMQ was designed to be lean and mean and not have all the baggage that was in the old I/O path. But as it turned out, we do have applications and use cases where some of that fat from the old I/O path is actually useful. So all this flurry of activity we see here is not actually new stuff. All that stuff there, most of it anyway, is us trying to kill the old legacy I/O path completely, but move all the functionality over to BlockMQ that we have use cases for. And so it's really just a lot of internal shuffling and plumbing and stuff going on. And so one of the major events the last 6 months or so is that we now have I/O scheduling capability in the multi-queue path. And people are going, why on earth would you want to do that? Well, there are use cases where you actually have multiple applications running on the same system using the same drive, and you need to have some way of preventing the noisy neighbor problem, to introduce fairness and that kind of thing. And that's where the Kyber I/O scheduler comes in. That's designed specifically for that use case where you want to introduce fairness between different applications running on the same system. So it took a lot of plumbing changes to make sure that we could plug an I/O scheduler into the BlockMQ because it wasn't designed to accommodate I/O schedulers. The whole point was to avoid them. The default is still not to have an I/O scheduler in BlockMQ. You have to opt in to select Kyber or BFQ. The default is not to do any I/O scheduling whatsoever, because that's usually the best thing for your individual NVMe drives. The other scheduler option that we merged is BFQ, Budget Fair Queuing. It's an I/O scheduler that's sort of a retake of the CFQ scheduler we had in the legacy I/O path. It's a very tunable scheduler, and it's designed for interactive workloads mainly. So think your desktop where you don't want your mouse movement to be jerky or your MP3 skipping while you're compiling the kernel, that kind of thing. So it's a very tunable scheduler, and it's probably a good fit if you have a budget laptop with a slow NVMe drive and that kind of thing, because it allows you to give good priority to the applications where you care about real-time response. Another new and exciting thing that has happened recently is support for polling. So when you have applications that are really, really sensitive to latency variations, sometimes context switches are extremely expensive, and sometimes it's just not worth it to send the I/O, do a context switch, wait for the interrupt to happen, and then signal completion. Sometimes it's better just to sit there and hammer on the CPU in a busy loop and wait for that I/O that you really care about completing in a hurry. So we added support for I/O polling, and Steven, who's down there somewhere, there he is gonna scream about that tomorrow. Oh, singing about it, even better. So if you are interested in that kind of thing, I suggest to go to the session. I think it's a general session tomorrow morning. Yep. So that's really cool, and we have various ways that Steven is going to tell you about how you can decide when it's better to busy wait and when it's better to punt it, and we can do averages based on previous latencies and that kind of thing. So it's kind of neat technology. And as I said, we just added support for secure encrypted drives with Opal. So those changes there are really what's happening in the block I/O stack. But those 600 commits that cost the peak there, it's really mostly housekeeping. As I alluded to, you can see that we have like this affinity between SCSI and NVMe and block I/O changes in the development activity. And I mentioned that we have this common block layer that's kind of unusual from an OS perspective. Most operating systems don't have exactly the same thing, where a lot of the core functionality is in a common layer, and then all the specifics of the transport protocol, whether it's SCSI, SAS, fiber channel, ATA, USB, whatever it is sort of hidden at the lower end of the stack. So we have a bunch of primitives that a lot of operating systems don't have. Several of them have a flush primitive of some sort, but we have something called discard, which is our way to deprovision a block range. And discard is translated into trim on SATA devices, deallocate on NVMe, unmap, or write same with unmap on SCSI. But from the file system and application perspective, you just call the discard ioctl or the discard call inside the kernel, and we will take care of issuing the right command for the device in question. And the benefit of having the abstraction is that if you then layer software RAID on top, or LVM, decryption, whatever you have, that translation is still working. So you can have a RAID that's spanning NVMe and SCSI and SATA drives and do a trim, and we'll actually do the right thing. So we try to build abstractions into the block layer and hide the implementation specifics inside the device drivers that are specific to the hardware and the protocols, and use at the bottom of the stack. So similar to that, and this is something we've added the last 6 months or so, is write zeros. We have this primitive that you can use to clear a block range. And what the best way to clear a block range is may depend on the device you have. If it's a thin provisioned SCSI device that guarantees that you're reading zeros back after the blocks have been deallocated, maybe that's the best way to zero the block range. So instead of having to write out zeros, the device will just say, oh, you told me to zero these blocks. I guarantee you that you're going to get zeros back if you read those blocks, even though I have no actual backing for them. So that works for NVMEs and SSDs and thin provisioned devices and so on. And the write zeros command can be used and is used by the file systems to clear out metadata areas and so on disk. And depending on the type of hardware and the properties of the hardware, we'll do the fastest zeroing we can of those blocks. Another special thing about Linux is persistent reservations. Most applications that use persistent reservations prepare SCSI CDBs inside the application and send them out to the hardware through SCSI pass-through in the OS. In Linux, we actually implemented support for persistent reservations as first-class citizens in the I/O stack. And that means you can have an application that uses persistent reservations, and it doesn't matter to the application whether it's actually running on an NVMe device or a SCSI device or what it is. You're using the persistent reservation primitives, and the I/O stack will do the translation into the appropriate commands for the device. And something I've been working on for a while is copy in and copy out to take advantage of the copy offload features that are in some storage arrays. Hopefully this code will land for 4.15, and it'll do the same thing. An application or a file system will say, make a copy of this block range in the most efficient way you can, and then the storage can do it without having to pull all that data into the OS and back out to the storage. So we're trying to build a richer set of operations into the block layer that allows us to take advantage of the hardware capabilities at the bottom without at the same time hiding the implementation details from the application. Another thing that's very actively being developed, and something I have been screaming about here at SDC for several years in a row, is hinting and streams. We at Oracle have a very extensive experience with hinting and streams, especially hinting as far as our products are concerned. We get really, really good results, and several of our product lines are built around the capability that the storage knows why the application is doing I/O, and that makes it much easier for the storage to make an intelligent decision about whether to cache or not cache and where to put the data placement and that kind of thing. And so some of the stuff that we have put into the kernel recently is a set of data lifetime hints. That's especially important on NAND devices where you want to co-locate things that have similar lifetime. And you will often end up, when you're writing a file, submit multiple I/Os roughly at the same time that belong to the same file, but you're constrained by the maximum I/O size of the device, so you can't submit it as one big I/O, plus the file might be fragmented, whatever, in the LBA space. But by using these hints, you can say that all these I/Os that have the same lifetime should probably go into the same bucket on the flash, and thereby reducing write amplification and making wear leveling easier. We also have hints that you can set on a per I/O basis that says this I/O is important and should be given high priority, and we plan on tying that into the I/O polling thing in the future. And we have a background hint that says this I/O is not important, it's the backup. Don't bother stealing I/O cycles from anything else. As long as it's done by tomorrow morning when we start the next one, we're good to go. And then in terms of the data lifetime hinting, it's currently implemented using the streams directives in NVMe, but the abstraction at the block layer really doesn't preclude other implementations. As a matter of fact, there are some devices out there that use the DSM flags in NVMe and SATA and SCSI to essentially provide the same capability as streams do. And so there's nothing that prevents us in the I/O stack from translating a hint about high priority or long lifetime for write data or whatever to something that can be expressed in terms of DSM hints or logical block markup descriptor indexes in SCSI. So we try to make it as abstract and generically applicable as possible. So in terms of that, so there's a lot of talks here at SDC about getting absolute maximum performance, best latency, specifically tuning, I'm looking at you, Matthias, something for one particular application workload. And that is great. And you're always going to be able to come up with a way where you can tune a particular set of hardware and applications to just completely rip at the expense of everything else. So with my maintainer hat on, I think it's cool, technology is cool, but with my maintainer hat on, I have to put something in the I/O stack that is applicable to everything from the wristwatch and the phone up to the hyperscalers. So the challenges I generally face is coming up with abstractions and concepts that work across a wide range of applications. And that may mean that you're not getting the 99.99999 percentile tail latency across the board, but if you're getting 95% performance across all types of applications, maybe we're doing the right thing. So the general approach is we try to do something that benefits everything, and at the same time we don't prevent people that want to hand tune and hand optimize things for a custom application, they can do that. So, zone block devices. This is something I hate with a passion. I've been resisting putting it into the kernel for years. And then finally last year here at SDC, I sat down with a couple of guys and said, okay, if we're going to do this, this is how we're going to do it. And so unfortunately, they did what I told them, and so I had no choice but to merge it. So we now have support for that. And so SMR drives are absolutely horrendous from a normal application and file system perspective, because you can only append to a limited number of zones on a drive at any given time, and that is very, very unfriendly to the way POSIX I/O works and how applications expect things to be working. So the stuff we put in sort of masks the effect of the SMR drives by providing a DM zone personality that essentially takes some of the zones away from the capacity, reported capacity of the drive, and provides a simple FTL that masks the effect of the SMR drive and allows you to put a regular file system on top of it. Right now, it works kind of, sort of, for the legacy I/O path, but as I said, we're trying to obliterate that. And getting SMR to work in BlockMQ universe is slightly more complicated, because all of a sudden you can have all cores submitting I/O to the drive at the same time, and so you need somebody to sequentialize that I/O very carefully for each of those zones. So that work is ongoing. Hopefully in 4.15 we're going to get that fixed. So on to NVMe, another area of very active development. You can see here that we merged the initial driver in 2013. The initial driver hooked straight into the top of the block I/O stack. It wasn't really a good fit for how we generally do things. And customers really wanted things that they expected to work on other block devices like SCSI and SATA to work on NVMe, like I/O statistics and being able to tune various parameters, I/O size, and so on. And the initial driver hooked into our top of the block stack into BIOS rather than requests. And it was very fast. And at the time, we didn't have BlockMQ, so it was really the only way to get better parallelism was to hook in that way. But then BlockMQ came along, and Matthias, again, did a tremendous amount of work to get the driver converted to BlockMQ, and that happened like 2015 or something like that. And so that was sort of like the second rework of the driver. And then what we should have been done. But then you can see the development activity boomed. And what happened was the third iteration of the driver happened because we had to accommodate fabrics. So the initial driver was very monolithic in the sense that it was written to drive a PCI device using the NVMe protocol. And then NVMe over fabrics came along. And we split the driver into a core protocol thing, akin to primary commands and block commands in SCSI, if you will. And then a PCI-specific portion that speaks the PCI queuing language. And then a separate driver for the fabrics RDMA binding that allows you to run NVMe over fabrics over Rocky and InfiniBand, for instance. That code went in about a year and a half ago or so, I think. And then this last year, we merged support for Fiber Channel NVMe. So that allows you to tunnel NVMe commands over a Fiber Channel fabric. And the TCP transport binding is in the pipeline. So there's been several talks at this conference about the merits of Fiber Channel versus TCP versus RDMA. And there are definitely use cases for each of those. You know, if TCP is probably going to be a slightly further out on the fabric capacity game where you don't have strict latency requirements. And then for stuff where latency matters, you would probably deploy Fiber Channel NVMe. And then for things where you're tightly coupling things in a cluster, that pretends to be one computer, maybe, the RDMA, very tight, low latency coupling, is probably going to be the game. But anyway, as a result of the third rework of the NVMe driver, we're now in the position where we can support all three. There's been several proof of concepts posted of TCP transport binding, but the official NVMe Express organization spec is not done yet, so they've just been proof of concepts, and we haven't merged them. Aside from that, the driver is pretty feature complete as far as 1.2 and 1.3 of the NVMe spec. We've added a lot of support for power management as a result of a lot of laptops now featuring NVMe drives instead of SATA drives. And as a result of a lot of consumer drives as well as enterprise drives having bugs, our quirks list is rapidly growing, where we're having to work around issues in this drive and that drive. Steven yesterday was super excited about how there's one driver and it works on everything. And I reject that universe. I wish it was true, but ASIC bugs exist, and we do have an extensive list of workarounds in the driver, and it's growing. At least it's one driver, but you know. Yeah. We also have support, as I mentioned earlier, for persistent reservations in NVMe now, using the common block infrastructure for the persistent reservations, and we have target support, which means you can set up a Linux box to export any block device on Linux, whether it's software RAID or whatever it is, as an NVMe target to another system over all the supported transporters. And finally, multipathing has been underway for a while. Christoph, who is roaming the hallway somewhere, has just posted a patch set that implements support. And this morning, a different company posted an alternate approach to multipathing. From a specification perspective, work is still ongoing in the NVMe Express Technical Working Group to define ANA, asymmetric namespace access. It's the ALUA thing for NVMe. So it's slightly simpler than ALUA was in SCSI. All the things that nobody ever implemented in SCSI has sort of been left by the wayside in NVMe, and it's a much simpler spec so far. So that is coming, multipathing support. And then the final topic is persistent memory. You see there was nothing for a while, and then Intel published the ACP NFIT spec, and off it went for a while, and it sort of plateaued for a little bit. Most of the core support for persistent memory is in the kernel. Thereby not saying there's not a lot of work to be done, but the plumbing is in place, and most of the efforts at this point is concerning how you handle flushes. So if you have an application that wants to manage its data structures in a way where it's guaranteed that there's not going to be any inconsistencies after a crash when the application comes back, it'll have to do cache flushes. And that interferes with the killer app that is files. Customers really like having files. We at Oracle, we have volume managers and stuff like that. You can stick into the database. People don't have to use files. And the first thing customers do is add files to that. So they can copy them and back them up and stuff like that. We have a file system that's built into the volume manager in the Oracle database that allows you to do that. People really like files. It's a good way to manage groups of data. You can assign permissions. You can assign ownership and that kind of thing. So a lot of applications, even though they might be block-based, would like to have files. And so we have this duality thing going on in the kernel where you can take an NVDIM and you can decide whether to carve it up or whether to use it as a block device. If your application, there has been lots of concerns this week from people I've talked to about persistent memory and how you have to rewrite the universe. You can still just use it as an SSD. And if it meets your performance numbers, go right ahead. You don't have to change your application. But if your application is of such a nature that it is a benefit to you to rewrite the application so you can manage things at a cache line granularity, I tend to think of it as 64-byte sectors because I'm a block I/O guy. But But if you can benefit from that, it's might be worthwhile to rewrite the application. You know, you're going to get very different latency characteristics from doing flushes at the cache line as opposed to typical 4K file system blocks. So we support both in the Linux kernel, and the little wrinkle is how do we deal with the fact that the sysadmin might be coming in from stage left and doing a copy on the file while an application has mapped that file as persistent memory. What if you move the file, all these things. So the way file systems currently work is the file systems hide all the effects of that from the application. You know, we can relocate blocks on the device. We can toggle pages read-only in memory, do copy and write. We can do all sorts of tricks in the I/O stack and the VM stack to mask the effects of that. But if an application is directly accessing the non-volatile memory and there's no second copy, there's no cache of that data, you're accessing the NVDIM page directly, then we need to have some sort of measure in place in which an application can tell the kernel, I would like to map this, and please make sure that the metadata is stable on disk, it's immutable, nothing gets changed. If the admin is doing something that would cause problems with this mapping, you will have to have a way to signal to me that the mapping of this file has changed and I may have to re-mmap this file. So there are currently two different implementations that are competing about which one is the right approach to go about this. One is called MapSync and the other one is called MapDirect. MapSync provides some of the benefits in a very easy to implement package, but I'm not entirely convinced that it's going to solve the performance problems for the applications that truly care about this. So I don't know if Andy's here, but he's speaking after lunch, so maybe it would be a good idea if you're interested in this to hear what Andy has to say. I assume he'll be covering these two calls. So this is like globally the activity of commits, the number of commits in the Linux I/O subsystem. So SATA, SCSI, NVMe over the last 5 years or so. You see we average about 2,700 commits per year in 2013, and we're now up to about 3,500 commits in the subsystem per year. And about 1,600 of those are SCSI, which explains why I never sleep. Because that's about 35 patches per week that I have to review and merge in SCSI. And it's mostly drivers because we have so many of them. But there's a tremendous amount of activity. And so if we filter out the drivers, right, the drivers are typically written by the hardware vendors for a particular piece of hardware. But the core code, block layer and SCSI and NVMe, we're maybe 10 people that are regular contributors to the I/O stack. So we're busy. Come help us. If you have problems, feel free to contribute. We could use more hands. Okay, that's about it. Questions?
So it seemed like you were name-checking a lot of those 10 people right in this room.
There are definitely quite a few of them here, yeah. Mm-hmm.
Does anybody have a question you'd like to ask? No? Okay, well, we're going to be serving lunch out in the mezzanine, so please join us for that. And don't forget, we have amazing breakout sessions this afternoon. Thank you.